of our 3-day workshop on statistics in data science and machine learning. I hope you had a very enriching learning experience on day 1. Today we continue the spirit of learning, and today's session, I'm very privileged to introduce to you Dr. Professor Gangadhar ND. He is a distinguished academician and an innovator in the field of computer science engineering, Ramaiah University of Applied Sciences. Professor Gangadhar holds a BE from Andhra University, MSc by research from Indian Institute of Science, and PhD from Ramaiah University. He currently serves as the chairperson of Committee of AIML Quantum Technologies at Ramaiah University. Since joining the university in 2008, he has made remarkable contributions, founding the Department of Computer Science Engineering in the year 2012 and being the chief architect behind several innovative UG and PG programs, including BTech in Computer Science Engineering and BTech in Mathematics and Computing. A visionary educator, Professor Gangadhar has designed and introduced over 30 courses at undergraduate and postgraduate levels, including pioneering courses on quantum computing and generative AI applications. He has mentored and guided more than 70 master theses and dissertations spanning in areas of causal machine learning, AI in healthcare, multi-sensor data fusion, security analysis, and performance optimization of network systems. Professor Gangadhar is also a prolific innovator, having filed 10 patents, and 8 of which have already been granted by the Indian Patent Office. His research interests lie in causal machine learning, AI in healthcare, and optimization and control of network systems. Above all, he is deeply passionate about pedagogy, believing that true learning lies in application of knowledge, where theory finds its greatest purpose through practice. Let us all join together in welcoming Professor Gangadhar NG. Please give him a round of applause. Sir will deliver the session titled Beyond Familiar Landscapes, Probabilistic Graphical Models. Over to you, sir.
Thank you, Sarista, for an introduction, kind introduction. I added a few things which I didn't write myself, so.
Sorry.
No, I added a few things which are, sounding better than what I wrote myself, so my savings. Yeah. Good morning, everyone, present here as well as online. So I don't want to again introduce myself. Today we are going to, I talk about probabilistic graphical models. Okay, so I think it's not very familiar thing for statisticians and probabilists, and maybe even computer scientists. Okay, so I thought I will take the opportunity that this is a workshop, not a seminar. So the caveat is, let me start saying that I'm not going to give an overview of the entire field. It's not possible in 1 hour. I teach this subject for 6 months, and that itself I struggle to finish, the course. In a sense, you don't go to the 40 years. But of late, I've been teaching this for some time. We have introduced this course in 2018, 2016, sorry, when we started AIML from university. But of late, I actually try, for the last couple of years, I'm using this in my research with my students. So, unfortunately, I will not be able to bring too much of that today. Okay, so what I thought was give an appetizer to this field, which actually combines both mathematics and computer science very well. Okay, so it should be interest to both statisticians, data scientists, and machine learning. In fact, I'll just give one, example at the end how this, can be used directly in machine learning to do something. Okay. So this overview. So I put myself. So we can go forward. Okay. So let me start with. So my title of the talk I gave was, beyond the known frontiers, beyond the known landscapes. So what I mean was, to do that, let me start with just surveying the landscape that we are more or less familiar with. Okay, Okay, so including the students here who have done a probability and statistics course already. So if you look at probability and statistics, okay, so it's about modeling and quantifying uncertainty, right? So that's the basics of probability and statistics. And not only just quantify what is uncertainty, but also the effect of uncertainty, both in real life, in real systems, or in engineering systems, everywhere. You want to know what is what the uncertainty causes, and maybe how to control it or how to increase it, depending on what you want to do with it. Okay, and to do any of those things, we need to actually to be able to estimate those. And a lot of things were talked about yesterday about estimation problems, where statistics comes and does a major role. Okay, so estimate the effects of uncertainty on systems from observations. So you either collect the survey data or make observations in a scientific lab, or just you got your data from some system. Okay, right? And then, of course, we write the hypothesis and verify those hypotheses. For example, yesterday also Dr. Suresh was mentioning. So, for example, you want to say that my manufacturing process is, has good quality. So that's a hypothesis. So you go and set up a testing, facility, statistical testing facility to actually start, to test that hypothesis and establish that it is actually true. Okay. Right, so that's very largely the landscape of probability and statistics. If you come to machine learning and data science, okay, it's taking the same maybe 1 lakh kilometer above, bird's eye view of the system, okay, of the field. Basically, machine learning data science do is mathematically model the data generation process. Okay, so this is how it is. It overlaps with statistics, but also differentiate itself from statistics. Okay, so we are interested in how the data gets generated. We develop a model and try to learn that model. Okay, so from data. So that's what machine learning does. Okay, in a larger sense, data science. Okay, so that raises a question. It will keep coming back to us. Yesterday also a couple of times this has come. So is it just applied statistics or machine learning and data science? I will not get into that, okay, but I think I've given enough hints about what my view on this is. But okay, so but it's a thought process you should keep in mind. Right? Okay, so useful question. And these two are landscape that we are more or less, if you are a computer scientist or if you are in a modern day scientist, so you'll be familiar with, or you should be familiar with. Okay, so. But there is, a lot of thing that comes from core computer science actually. But this is also a mathematical subset, okay? So which is graph theory and graph algorithms, and they find, applications all over, computer science, and a lot of engineering systems where, optimization, okay, comes in. The power is why graph theory comes into play is actually because graphs model relations. Okay, so in general, if you want to relate, most of the systems are subsystems or variables which are related to each other, and any study will want to actually analyze that relationship and capture the relationship. And graph is the natural way. Okay, it's actually in computer science we call it data structure. So that's a natural model for actually capturing relationships between variables. Yeah, in statistics also we do it, but that is in terms of probabilistic relationships. I will come to that in the next slide maybe. But this is core deterministic relationship between variables or data features, what you want to call it. Okay, and then so they can be used to quantify and estimate relationships for better. That's what graph algorithms do. And more importantly, they allow us to discover emergent properties. Because once you connect things, or once there's a multi-dimensional system and they interact with each other, you get what's called emergent properties. All complex systems have emergent properties. Properties which are not present in any one of the subsystems. Just because they connected, you'll get new properties. Okay. So that's a lot of graph algorithms are actually used to identify that. Okay, for instance, in Facebook, friendship networks are there societies which are formed. Okay, so that's an emerging law, right? Sorry. And so this that's a kind of domain view, but actually if you look at techniques or what kind of problems people tackle in these probability statistics, machine learning, data science. Okay, so I would like to put them in this following way. One is a lot of that is data driven. Okay, so statistics, of course, they are all about data. Similarly, okay, so similarly, machine learning and data science is also about data. Okay, so predominantly, okay, so the difference between these two is, the approaches or philosophies is probability in statistics. You generally move from model to data. Okay, that means you already have some idea about, okay, I have these random variables and I think they are linearly related or they may be having some correlation. I want to find that correlation. Okay, so that's so that's how we actually try to look at the problem. Whereas machine learning, okay, so primarily tries to do learn things, learn the model from data. Okay, of course, big caveat. There's so much overlap now actually that this dichotomy is not 100% true. A lot of machine learning does model to data. Similarly, statistics also there from data they construct models. Okay, so there's a lot of overlap in this thing. But just to understand and keep our understanding, in a particular perspective, I wanted to highlight that way. Then both of these sciences do what's called inductive reasoning. Okay, so we all know deductive reasoning. That's the engine or the powerhouse of all our science and engineering. How we build systems. I mean, again, mathematics. Okay, so much of it is deductive logic. That means you start with some known things, okay, and then try to deduce, okay, some phenomena from it or some consequences of those things. For example, if you know there is something called gravity, you know that Earth go around Sun, for example. So that's a deduction, right? So whereas inductive reasoning actually takes a leap from known to the unknown. Okay, so that's induction. Mathematical induction, all of you have studied, for instance. So that is actually you observed only property of all natural numbers, and a few all finite sets of natural numbers, and you want to deduce that the property holds for the entire set of natural numbers. That's for the infinite set. Okay, so that's a classical inductive reasoning, and both the sciences, and this is a part actually of both machine learning, data science, and statistics, is that they actually do inductive reasoning. For instance, in statistics, we collect data which is a sample. We never collect the entire statistics of all the people in the population or the objects in the population. But most of the statistics are about what happens to the population. When we say what is the average age of the people in India, for instance, nobody goes and measures everybody's age. We do a sample and then try to guess or estimate the age. That's a typical inductive reasoning. It's called inferential statistics. Similarly, of course, machine learning data science is all about inductive reasoning. Okay, so you use some training data, for instance, and learn the model, which should hold for all data which you have not seen also. Okay, so this is another, what we call phenomenology or the philosophy in which we actually work in these fields. And both these sciences use similarity, okay, mathematically defined similarities. Okay, so for example, probability in statistics, covariance, correlation, all are similarity between random phenomena, random elements, or random variables. And machine learning data science is all about pattern matching, classification, clustering, all is about similarities, right? And this similarity need not always be in this familiar known stuff, of course. Functional similarities, for example, regression is the version of similarity between two continuously variable functions, okay, that's variables, right? So that's something that's something I try to set up a thing because we wanted to see what landscapes we are very familiar with, and let us try to be a little bit beyond those landscapes. Okay, of course that's a very major statement. So try to do some justice to it. Okay, so before doing that, one, let us try to do a very, because it's a workshop, so you can actually try to do this exercise mentally at least. So I give you a probability distribution, which is the joint distribution, right, between x and y, two variables, simple, both are binary. They take true or false values, and let's suppose that's a probability distribution on the right side. Okay, so on the last graph, can you identify some structure in it? There are some four numbers, but can you see some structure or a pattern in the numbers? Not the familiar, things like arithmetic pattern or geometric progression. That doesn't work here. Okay, it's a multiplicative pattern.
If the false in the right value, the rank is reduced.
Okay, I do not want qualitatively fine. Okay, but it does. Okay, so I really want a quantitative answer. Okay, so it's hard because it's actually I'll tell you what's the pattern. Oh, sorry. Oh, what? It's actually the pattern is the probability distribution actually splits into two. It's a product distribution, px and py. Okay, so the 0.32 is a multiple of two numbers, 0.08 is a multiple of two numbers, like that. Okay, and where? Can you guess what those numbers are? Now there is a major hint given. So for the people who are experts who are listening online or something, so I've decided, made a very conscious decision that I'm going to run my workshop like this. So I'm not going to do a seminar which is going to tell what's PCM and entire stuff. Okay, so try to get to understand what PCM does and leave it as an appetizer. So anybody interested can go forward and learn. Okay, so next. So yeah, it's very hard. Okay, so come down. One more. Yeah. This is the actual distributions. Okay, if it is 0.4 and 0.6, x distribution y is 0.8 and 0.2, you can actually see that true is 0.32, etc. It's easy to verify. Okay, but it's very hard to actually guess that. Okay, and this is what at the core of much of the statistical learning algorithms. Okay, so probabilistic learning algorithms and probabilistic graphical models we try to from given some, in fact we are going to do from data. Okay, so I know some measurements about x and y, I want to get this and I want to actually try to see these structures. Okay, the entire talk is going to, actually half the talk I am going to convince you that the structured learning is going to be helpful. If you do learn structures like this, for example, if I know x and y are independent, you can do a whole lot of stuff. In fact, at the modeling level, if I know that they are independent, I can make decisions on x without bothering about what y does. Okay, so because they are independent variables, I can change x the way I want. I can control y, etc. So there's a lot of stuff that comes in if you learn structural stuff. Okay, and that's not the only thing. If you learn structures, we can do computation very efficiently. So that's where graph theory comes in. Okay, so that's entire, in addition, that's what I want to convey in this talk and in this workshop. Yeah, next. So okay, I do not want you to guess, this is even harder, but just wanted to give you a flavor of what happens if there are three variables and I want to get a structure. Okay, so please enter next. So here, the structure is x and y are independent, not by themselves, but only when we know z value. Okay, so that is given by this notation, x is independent of y given z. Okay, so yeah, just you can show the next one. So obviously this is going to be useful for us. So the distribution actually splits into these factors, which is Pz, Px given z, and Py given z. Okay, so this is what's called chain rule, right? Chain probability. Okay, so yeah, next. So here is the actual full-fledged answer. That is Px given z is that, Py given z is that distribution, Pz distribution is this. So I cheated, obviously I generated this from that. Okay, so I assumed this product and generated. I didn't discover them. Okay, so I didn't go this way. So yeah, it's nice. Yeah. So what we have seen is okay. So maybe this real starting point of our workshop is distributions sometimes can be factorized. That means put into a multiple of factors. Okay. For example, if your model has n variables x1 to xn, for example, it could be suppose you are looking at some patient database. It could be age, blood pressure, or other things that you have measured, okay, x1 to xn. Obviously they are related, okay. So that's why they will have what's called a joint distribution. That means they have a distribution among, if you consider all of them together as a vector or combined random variable, okay. So they have a joint distribution. One of the things with the joint distribution is it grows exponentially with the number of variables. Suppose you have seen, right, if there are two variables, joint distribution has 4 entries, even they are binary random variables. And if there are 3 of them, it's 2 to the 3. If there are 2 to the n rows will be there. And in computer science, the first thing you see 2 to the n, you have to stop. Okay, if you are not stopped, then you are not a computer scientist. Okay, if you see exponential, I cannot work with them. Okay, so the first problem with joint distribution is just storing them is, suppose I have 100 variables in my system, which is quite common. Okay, it is 2 to the 100. It's almost the same, it's the order of magnitude of the entire, stuff in the universe. So you cannot store. Okay, so you should pass. So you're not going to work with joint distribution just blindly like that. Okay, so you cannot. So the entire purpose of probabilistic graphical models initially is to figure out how to work with such large distributions without actually storing and processing individually, the entire tables. Okay. So obviously, how to reduce that? We can reduce only if there is some structure. Okay. So that is if you can factorize. Structure in probabilistic and statistical sense is independencies or conditional independencies. Okay, for example, x is independent of y and w given, let's suppose, some z variable. Okay, if you can find out that's a structure, you can use that structure to actually figure out how to do the factorization, like we have done in this two simple examples, right? So factorization is a real answer. Okay, so we need to figure out conditional independencies in our variables and use it to reduce our size of the structure. Okay, so let us see how that reduction can be done. So one first way is actually using chain rule of probability that we have used already, right? So same thing here. So here is a general chain rule. Probability of x1 to xn is probability x1 times probability x2 given x1 times probability x2 3 given x1 and x2, etc. Right? Probability xn given x1 to xn minus 1. So this actually, if you think a little bit, it doesn't save anything. If you just blindly, this is the only way you can write it. Okay, because if you see the last one, xn given xn x1 to xn minus 1, it already has n variables in it. So the probability joint distribution table will be as big as, it will also be 2 to the n, as big as this. So we are unnecessarily introduced some stuff and we didn't save any space. Okay, the whole thing boils down to be useful if probability xn given x1 to xn minus 1 can further be reduced. Let's suppose probability xn given, let's suppose x3, x4 and x5 only. Okay, that means xn depends only on 3 or 4 of them, a small number, not the entire x1 to xn minus 1. So if each of them is smaller, that means there are local dependencies as we call it, then we can take advantage. Then we can actually reduce that. Because that will be only 8 rows in that case, or 16 rows. Right. So first thing is to use this, but it is advantageous if it actually has local dependencies. Next. Another, of course, is even more general way of factorizing. It's called factors in statistics. I think tomorrow or today afternoon you have one talk in which they will talk about factors. Okay. So this is kind of familiar to statisticians. Okay. So and this comes from actually physics. Okay. So it's called no, so what happens is this, instead of considering a particular type of factors which are given by chain rule, they can be much more general. Okay, X. And that need not depend on only one or two of them, they can depend on different ways. You can have some K functions which are called factors. Okay, and then they multiply and give you your P's. Okay, now the factors need not be even, okay, so probabilities. Okay, they can be just numbers, as long as they are positive it is fine. So if you have those kind of functions which are positive functions, then I can actually normalize it to get my probabilities. Okay, that's why this Z is a normalization thing. It's called partition function. Comes from physics, particle physics background. Okay, and we'll see why it's called a function a little later on. Okay, so near the end of our talk. Right, so this is a more general way to partition. For example, if you take phi 1 to be px1, phi 2 to be px2 given x1 like that, and phi k equal to n, obviously that one I can recover, right? So and then z becomes 1 because all are probabilities, so they add up to 1. So it's they know z is becomes 1. So this is a particular case. So conditional probability distribution based factorization is special case of general factorization. Okay. And next. Yeah. So, as I mentioned, this is at least efficient in storage only if this happens, if the dependencies are localized. For example, in the case of conditional probability distribution, each xi depends only on a few other random variables, right? On the other hand, if you have general factors, suppose I put f of every variable, right, x1 to xn, but suppose f1 depends on, sorry, phi 1 depends only on, let's suppose x1, x3 and x4, and then phi 2 depends on x3 and x4, x7, like that. So they have small number of variables in their scope, as it is called, as a function. Then again, we have some saving possible and we can use that structure. Okay, not only for understanding the system, explaining the system, but also computationally you can actually reduce the size, and so you can use it. Yes. Okay. So that's kind of set a stage for us to actually look at something which is not so familiar. Okay. So then the purpose of this workshop, this session, is that to familiarize you with this idea that we can bring in graph theory, okay, into these statistics, okay, and do some useful stuff, and not only computationally, but actually, as we'll see a little bit, unfortunately we're not able to see that very well, okay, and in full scope, it brings new tools, okay, and answers new types of questions, okay, so that's thing. So right, for instance, the factorization, actually, as I mentioned, it is what's called structural. Okay, it is because it tells something about the nature of the dependence between the random variables. For example, x is independent of y given z tells something about the structure of the system, how they are structured or related, right? And factorization actually tries to capture it. If you use CPTs, that means conditional probability distributions, okay, you will get what is called Bayesian network. Okay, so I will not go to network. We will get, okay, and that structural relationship I can use a graph to represent that relationship. Okay, so so if you use a graph which is built on conditional probability distribution based factorization, you will get a directed acyclic graph, and which becomes what is called a Bayesian network. And on the other hand, if you use more general, okay, factors which doesn't have that probabilistic interpretation of conditional probability, then you'll get more general graph, which are undirected graphs, and such models are called Markov network models. So here is a couple of nice examples for this. So okay, before anything, actually graphs actually gives a lot of transparency, very easy to understand. Okay, So you'll see that. But instead, I don't have to spend much time to explain you what these two networks mean. So the first one says, and obviously it says, flu or hay fever, okay, seems to be obviously related to the season. They are seasonal. Okay, flu generally comes in damp, cold time. You generally get flu, and warm, dry weather time. If you still haven't got viral infection, you get hay fever. You'll have running nose without muscle pain, for example. Okay, so if you have summer flu, which is mostly hay fever, right? So obviously it depends. Both are seasonal. Okay, and then if you have flu, you may have muscle pain and congestion as symptoms. Whereas if you have hay fever, you only have congestion, no muscle pain. Okay, so this is a relation. Okay, so the season seems to affect whether people have flu or hay fever, and having one of these affects which symptoms you show up with. Okay, right. So that's what's so in this case actually this is actually what is called causal, in the sense season seems to cause which of these things happen and which of these disease causes symptoms. Okay, so that's a network. Okay, so we will see that, for example, how conditional probability distribution comes in. Suppose you have S, F, H, C, and stand for those. Okay, the first letters of the variables. We can see that actually season is independent of everything. Then I use just simply, okay, this F depends only on S, H depends only on S, but C depends on both of them, M depends only on F. So instead of writing M depends on F, F and H, I simply wrote or S, for example. I reduced that because they are no longer dependent, right? So this is what I'm saying. So we can actually, in this case, the probability, any variable is dependent only two, at most two of them. Okay, not all of the rest. So for example, multiplicand doesn't depend on the rest of the four. Okay, so similarly, the other one is actually what's called a student confusion network. Okay, these are standard textbook examples. Okay, so they have names like this. Okay, so flu network, confusion network, etc. Okay. So here, for example, there are four students, A, B, C, and D, and A and C don't talk much to each other, and similarly B and D don't interact with each other much, but let's suppose they are attending the same course. Okay, and obviously they discuss something which they don't understand. Maybe they go and discuss. Whom they will discuss? For example, A has a doubt, he will go and discuss with B, and B, similarly vice versa, and okay, so that's a network. Alright. So in this case, you will see that C, for example, suppose A understood something, and does C get to know that, or understand the same way, or agree with that, disagree with that? What chance he has? He has that chance only if that passes through D or B, right? So A to C, there is no direct path except D or B decides to share, or he has a chance to discuss with B as B or D. So this can be expressed as follows. Okay, so that means these A and D are related, A and B are related, C and D are related, C and B are related. Okay, and so that there is no direct relation between D and B, for example. Okay, nor A and C. Okay, so I can actually write this relation as a factorization like this: B, A, B, C, D is phi 1 times that relation, whatever numbers you want to put. For example, A and B are real close friends. Okay, whatever A understands, B may understand better. So I put 100 there. Let's suppose A and D are not so close, so they don't meet each other. Let's suppose D is a hospital, A is a hospital, B is a day scholar, etc. Then I can put less, maybe 5. That depends on their relation, can also be quantified the way which I want. I can give some quantification to it and then write this. Okay, so those are the functions, and then you have a factorization. Okay, so and as you see, models. Okay, brings transparency. Okay, so we have seen the network. Okay, so that is structural, but that's not enough, right? We have actual probability somewhere. So if you join all those probabilities, this is how the full network looks like. Okay, nobody generally draws this, but this is visualization of that, right? So that's a graph. This is a different network. It's called student difficulty network. Okay, so and grade depends on difficulty and the student's hard work or intelligence, and similarly his gate score or SAT score depends on his hard work, not difficulty of the exam, or I mean not the difficulty of the term test, right? And the grades allow professors to write recommendation letters. Okay, so this is a student network. It's a small part of it, slightly more bigger one will be there. So so probabilistic graphical models, okay, so bring in both the graph structure and the what is called parameterization. That means the probabilities involved with each of the variables. For example, in this case, the difficulty has two numbers associated with it. That's a vector of 0.6 and 0.4. Similarly, intelligence has, let's suppose, highly intelligent, not so highly intelligent, or difficult, not so difficult. So we decided to make it binary. And grade, maybe there are three grades. Okay, so that's a table. That's a conditional probability table of grade given difficulty and intelligence. Similarly, SAT score depends on intelligence. So these are conditional probability distributions. Okay, so this is how the entire probabilistic graphical model looks like. It has a structural thing comes from graph, which could be a DAG, or a directed acyclic graph, or it could be a undirected graph. Right, so that's what is meant by probabilistic. Yeah, next please. So just to compare and go back and look at the BGMs for this. So those are the graphs. These are the factorization, and the independences that we can actually figure out from that. Okay, so are these. For example, F is independent of H given S. So given the season, whether suppose you know it's winter, okay, then whether you get flu or you get high fever are independent of each other. Okay, so those kind of are embedded into the model. That means you have decided that this is already true. Okay, so unless that is true, you will not draw that graph. So unless you have a domain expertise, okay, you will not build a PCM structure. We'll come to that in a little bit, maybe a couple of slides later. So, can we still build the structure without having domain expertise? Using, of course, everybody wants to use machine learning, or this thing can be discovered. Okay, right? You can do statistical estimation to do that also, but we will not get into that. But it can be done. Okay, so I'll just mention it how to do that. Similarly, if you look at the other side, there are independencies. For example, A is independent, A and C are independent of B and D. Okay, so sorry, A is independent of C given B and D. Okay, so that means if B and D decided not to talk to convey what A conveys to C, then A cannot do anything. He can, even if he wants to transmit it. So right, that's what is meant by that independence. Okay, or C doesn't get influenced by what A's understanding is if B and D don't cooperate. So that's what is meant by conditional independence there. Okay, so and this factorization and independence actually are dual of each other. That means if you know the factorization, you can identify the independences. If you know the independence, you can do the factorization. We have done the other way till now. Actually, it's also possible to move from factorization to independence. Okay, so I'll just touch upon that a little bit. But before that, it's not only what you call modeling way or understanding and explanation of the system. Graphs help and graph models, but also reduce the size. Okay, that's our initial motivation, right? So, for example, in the right hand side, okay, in the Markov network, the reduction in the total number of parameters stored. That means the numbers you have to store, right? All of them. So it reduced from 15 to 13. If somebody is interested, please figure out why it is 15 and why it is 13. Okay, so that's a small exercise. Okay, with 4 of them, all of them are binary random variables, whether understood, not understood. Okay, so that's what it is. So there should be 16 numbers, but I wrote 15 because the probability distribution, right? One number I don't need to store because 15 if I add, I will get the last one. 1 minus the 15 will give me the last way, right? So so with this, factorization, I need to store only 13 numbers. So with 4 and very small network, you could save how much, but you can actually go, if you have 100 variables, this saving could be much higher. In this case, it's much more dramatic. So original is supposed to be, actually 63. Okay, you go and calculate why it is. Season, I took it as 4 variables. But rest and all are binary. Flu or no flu, hay fever or no hay fever, no muscle pain or muscle pain, congestion or no congestion. So with that I should use 63 numbers. Okay. But when you use the factorization and I need to store only 19. For example, this needs 4, this needs 4, this needs, this needs 4, this needs 3, and this needs 4. Okay, so I figure out like that. Okay, so why you can do that thing. Okay, so that's a small exercise later on. Yeah, but before we actually look at Bayesian networks and Markov networks in little detail, it's not that you get it doesn't come with some caveats. Right? You should know that they also have certain power of expressing something. Okay. So for example, if I have some factorization in my mind, that means I have 3 features of some system or 3 of a, for example, they may be, for example, height, weight, and what else? Maybe hair color. Maybe they are independent of each other, jointly, let's suppose. So I have this understanding and I have this factorization in mind. Can I build a Bayesian network graph? Unfortunately, we cannot. If you try any which graph, what happens is you will not be able to satisfy this any which way. Okay. A Markov network, you can actually do it pretty easily. I forgot to actually draw it there in the next slide, but I didn't draw it. Okay, so here that network captures what is this factorization. Okay. On the other hand, if you have this factorization, which is our familiar chain rule factorization. Okay. So obviously, I know we have this is the first one and this is this. Right, px, py, and pz given x comma y, right? So that's the chain rule. So this captures, so Bayesian network captures that, and not only that, suppose I have an additional requirement, x is independent of y. Suppose you have only this one, I can actually capture it the Markov network. So this is the equivalent Markov network, which looks exactly the same without the reduction. If we go and see, actually, it's you can build a Markov network that exactly captures the same thing. But suppose I have an additional requirement where x is not only this, x and y are independent also. Okay, so then this network cannot capture this. Okay, so this fails. So this still holds. So it's not that we can actually think of any kind of relation between variables and think that we have a network. Okay, the reason is actually now something which I am not going to cover much is every graph comes with a built-in set of independencies. Okay, so once you choose a network, it comes with a whole set of them. Suppose that whole set is contradicting what you have in mind, for example, then obviously the network is not useful. Okay. So just before we actually go, there is to keep in mind what you are when you draw a network, you should know what it implies. Okay. Okay. So I put this slide for 2 reasons. One is to wake you up. Second is if there is somebody in the audience who is still afraid of mathematical symbols, okay. So one way to get rid of that fear is to stare at it. Okay, face your fear. Okay, work with the symbols, you will get out around that. Okay, so that's what I want you to do. Okay, so maths is a beautiful language. Okay, learn the language. Okay, so symbols are a way to write, just to write, right? So it's a small effort you need to put in to write symbols. Once you start writing the symbols disappear. The language words stay in mind. Okay, so like natural language. When you speak in the beginning, of course, writing A, B, C, everything is difficult. Okay, we spend a lot of time doing that only without forming words. Okay, so but once your words are speaking, the ABC comes automatically, right? So I want you to become like that, especially the young students. Okay, and obviously some of the old people are also afraid of mathematics. Okay, so hopefully not this audience because these are statisticians. So, alright. So suppose now what you can do with these networks? Okay, we have defined some networks, and what can we do? Okay, so in probability statistics, what you do is called inference, right? So is what is called probabilistic inference or statistical inference if you want to call it that. Okay, but it's called inference. It comes from the word inference comes from the logic. Okay, so you should be able, given a statistical system, you should be able to make meaningful conclusions from it. That's called inference. Okay, so in logic, right? So given, let's suppose I have some variables x1 to xn. Okay, here some 5 variables are there, and let's suppose I have what is called evidence variables. So that means some of the things I know. Okay, and query variables are something which I do not know about, and I want to know what are the values of those q. Okay, given some evidence, some values of evidence, right? So we have many ways in which you can pose this problem or pose this query. One of the simplest way is called probability query. Also, I mean, it actually is called posterior probability. Okay, so if you are into, so it is actually the probability that q takes some value q given evidence takes a value evidence. Okay. So, for example, in this network, my evidence could be that patient has come up with muscle pain. Okay, so is false and congestion is true. That means person doesn't have muscle pain but he has congestion. That's the evidence. Okay, let's suppose the query is it a flu? Okay, or is it hay fever? Okay, let's suppose these are only two possibilities for us. Okay, so what I want to know is the query variable is flu and whether it is true. Okay, the value it takes is true. So the probability query, I should write it as probability flu is true given muscle pain is false. Okay, and congestion is true. Okay, right? That's the probability query. I want to calculate the probability, right? So by the way, again, small exercise, mental exercise. What can you guess that probability? What's the probability the person, I know flu is true given muscle, there is no muscle pain but there is only congestion. From this figure, in the interest of time, actually it's nice to do this exercise. Actually, if you see muscle pain happens only if it is flu but not hay fever and the person doesn't have muscle pain, congestion happens in both the cases. So it's very clear that the person doesn't have flu, it's only hay fever, right?
Person having the flu only having the muscle pain.
He has muscle pain and congestion, but if he is having hay fever, only congestion, no muscle pain. So obviously he has presented with no muscle pain and congestion, so obviously it should be hay fever. Correct? Yes, if it is a deterministic system. Okay, it's not necessary that just because you enter everybody gets flu or hay fever, right? So there are probabilities. Okay, whole set of probabilities involved. Just because you have flu doesn't mean that 100% of every patient who has flu doesn't have muscle pain. Okay, so I'm sorry, and doesn't have if every 100% patients of hay fever doesn't have muscle pain, that you cannot tell. Some of them may develop muscle pain. Okay, so it's not 100%. All these are probabilistically related. So you cannot say that the probability is zero. You have to sit and calculate with the known probabilities. Okay, so that's what happened. Okay, so right. And then another thing for the thought process, think what does doctor does diagnosis, right? Like this, does he do or she does, or how else does he does? Think of that. Okay, there's a lot of yes and no in this answer to this question. Yes, doctor does this kind of investigations. Okay, but may not be using probabilities all the time, but they also use probabilities. Okay, yeah, there's a 50% chance that the person has, if he has hay fever, that person doesn't develop muscle pain and so on. Okay, and then the next type of probability queries are actually what are called maximum. Okay, so the bigger name, maximum a posteriori probability, or simply called MAP queries. Okay, so what it means is, okay, so I'm given some evidence, just like in here. I do not want to know the value of the query variables, like in the previous case. I want to know which is the most likely value that the query variable takes. Not a particular, suppose if you give me let's suppose a particular true or false, that is first query. But suppose I want to know whether true is more probable or false is more probable. Okay, so that's what's map query. So here is example. Okay, for example, same evidence, E is same, but suppose I have my query variables are season, flu, and hay fever, and I want to know what are the most possible values that I can assign to. Suppose a student patient comes in, I want to assign, okay, flu is false, hay fever is true, and season is summer. Most likely, that's what I expect. Okay, from the general understanding of statistics. Okay, so that's what's called a map query. I should be able to calculate and find out what is the most probable values. So every day, this is what you have evidence, and you want to know what caused that evidence, and what is the most like all the time. If suppose you go to court cases, this is what they do all the time. Somebody got murdered, and they want to figure out whether the person X has done the murder or not. That is probability query. They have some 5-6 suspects. They want to know who is the most likely suspect. That is a map query. Okay. And marginal map is you generalize it. Not on the most of the time, patient or doctor is really interested in what is season. They already know what season it is. So I only need to know set of values for flu or hay fever, right? So that's a smaller subset of the entire remaining non-evidence variables, right? So that's a map query. So its maximum is called R max, that value which takes that, right? So now these three queries are standard queries because computationally they are different. For example, second and third are actually more or less the same. Second is a special case of third, right? So map is a special case of map. But computationally, map queries can be computed much faster and much more efficient than map queries. Okay, so that's why there are three different cases, right? And again, using graph algorithms, this we are not going to touch upon, which is we can get orders of magnitude faster algorithm than simply working with the joint distribution. Okay, so understand that. Start 10. 11. Oh, right. You great. Okay. So before again seeing some useful things about this Bayesian network, one thing we want to know is all are fine, but we are in data-driven world. Whether you are data science fellow or statistician or machine learning, okay, can we construct these PCMs from data? Okay. For instance, you will turn out that suppose I have collected 1,000 patients data about season, when they had the flu, or whether they had flu or hay fever, or whether they had muscle pain or not. All the data are collected, right? People have tens of thousands of such data, right? Could we construct that network and its probabilities from that data? Okay. It has two parts, obviously. First part is the easier part is getting those probabilities. Okay, flu is dependent on season. Suppose season is winter, there's more chance of getting, so maybe 0.9 chance of getting flu rather than 0.1 chance of getting hay fever, or not getting hay fever. Okay, so that parameterization is easier to understand. In fact, it's basically plain old statistical estimation. All you need to do is estimate the parameters from data. Okay, you can use what is called maximum likelihood estimation or Bayesian estimation, and all do very well. And this very standard, well studied, well understood problem. Okay, and then we have learning the structure. So if you can go back once, go back. Yeah. If I tell you this, everything seems fine. Suppose I don't have this figure. Okay, all I have is patient data. Figure this out. That's the problem of structural. And as we have seen right earlier also. I have given you some table and I want you to figure out whether you can find whether there is any structure. So that's the structural learning problem. It's obviously much harder. Okay, and there are no unique solutions. Okay, so we use information theory and a whole lot of other stuff to actually figure out what's a good structure we can learn from. Okay. Yeah, please. Right? So that's a structural learning problem. Okay, so these are two parts of the problem. Okay, so one is statistical, another is a lot of information theory and graph theory is involved. Okay, so similarly in each of these even learning from data, graph-based algorithms do much better because they can actually exploit all the structure that may be present. Okay, so while they actually pick up the network. Okay, and finally, how does one come up with that structures? Most of the time, it's not that blindly you learn from data because, as you mentioned, they are generally not unique. So you get all kinds of structures which may not make sense. Okay, so most of the time, actually, what is done in real life is you sit with a domain expert and draw that network. For example, doctors know that in a winter you get flu and you get hay fever in summer. Okay, so they already know these dependencies, right? So that's the structure. So initial structure at least is built by domain experts. Maybe it can be refined using data collected. Okay, so you can refine your data. I mean structure from your data, and then of course you estimate parameters. This is purely statistical. So you collect more data, you get good parameter estimate. That means you know what probability that hay fever is present or not in people in winter in this region. Okay, so that's how actual real models are built. Okay, so it's not only data driven blindly. We generally make use domain expertise to build the data model. Okay, yeah. Okay, so let's okay, I'll spend some almost roughly equal time on these two couple of models. Okay, so Bayesian networks and Markov networks. Okay, so as we can. So as we have seen already, this is another example. Okay, so this is what's called sprinkler example, standard textbook example. So if it is winter, the sprinkler, may be on with less probability. Obviously, if it's not winter, then the sprinkler may be on with more probability. And if it's winter, it may not rain much, unless it is Bangalore. Okay, so right, so you have some probabilities, and grass on the lawn is wet if either it rains or sprinkler is on. On the other hand, road is wet only if it rains. Obviously, a sprinkler you don't wet your road. Okay, hopefully. Right? So this is called a sprinkler network, and that's a parameterization. Let's suppose that's one parameterization. That means that's such time distributions. Next, next please. Okay, here is a full description of the Bayesian network. Okay, so it has a DAG G. Okay, defined over the variables x. Okay, so that means the Bayesian network consists of G and a theta. Theta is a collection of those conditional probability tables as they call. Okay, that is a network parameterization, right? So each table is collected, theta 1, theta 2, theta like. So, and the thetas are generally expressed in terms of x given u. Okay, x is a variable and u are the parents because it depends only on the parents, right? So that's a parameterization. So to do that, we define what are called parents of a variable, descendants of, these are all graph theoretic, right? So parents of variable are something which are directly connected to that node, right? Through a link, okay, directed link. Descendants means anybody who is below, okay, which can be reached from that node. And non-descendants is which cannot be reached from that node, right? So if you have that, then you can define, okay, so the entire CQG structure and all. But there is one important type of Bayesian network which is really what we have been seeing most of the time. Okay, it's called causal networks. That means the relation is not just probabilistic, that x and y are related or x is independent of y given something. It also encodes what is called cause and effect relationship. For example, season affects whether you get flu or hay fever. That's a causal effect. If you have flu, you're going to get muscle pain and congestion. That's again a cause and effect relationship. And Bayesian networks are not necessarily that only. But Bayesian networks can involve anything actually. Okay, so but most of the time they are used to encode causal networks. Okay, so that means the parent variables are the direct causes and of the variable, and variable actually the effect of the variables are seen by all its descendants. Okay, so that's what's called a causal network. Okay. Just to give a flavor of what is done. Okay, so this is not complete. Okay, but suppose you are given a network structure, as I mentioned, that captures the structural relation between the variables involved, right? Given a graph, we can actually read out those structural independencies. One of the way to do is using what is called write down what are called Markov independencies, set of Markov independencies, which is given a variable,
its parents and non-descendants. Okay, given the parents, if you know the parents, what values it has taken, or okay, then V and non-descendants are independent of each other. Okay, so they are not connected. Okay, they don't influence each other. Okay, so that's written that way, or when generally people use this notation. Under the graph, if the graph is true for us, then we, the parents and non-descendants. The middle thing is a conditional thing that is given. We and non-descendant are separated by these parents. Okay, they are not influencing each other. Okay, and this set of independence we write for every variable. It's called Markov. Okay, so in causal network, what it means is, given the direct causes, okay, a variable is not influenced by any other variable except maybe its descendants. Okay, so that's the meaning of this. Okay, so here, for example, if you use a Markov and write down all the Markov, for example, what I have taken is, the first one is take A, alarm A, and then write down the Markov equals, find its parents, find its non-descendants, say that C is the descendant, okay, and B are the parents. Sorry, they are the non-descendants, they are independent of each other, right? So given A, sorry. Yeah. So if I write for C variable, the parent is A, and non-descendants are B and B, E are non-descendants. So C is independent of B are given its parent A. So that's the first Markov relation. Similarly, if I write for E, C is not dependent or independent of B, E, R given A. If you know the parent, parent only influences. Once parent's influence is known, other guy's influence you don't need to know. Okay, so there's no more influence, additional influence. The influence through A only. So if you already know the influence of A, okay, for example, if it is about some secret being passed. Okay, suppose A has already passed the C, it doesn't matter whether E passed to A or A passed to B passed or R didn't pass. All it doesn't matter, right? So that's how it is, right? It's the information flow. Okay. Here it's probabilistic information flow, but same logic. Okay. So you can write down such inequality. There's a whole lot of them. I didn't put them here because I know that I'm going to run out of time. Okay. So there are in fact there is a beautiful graph algorithm to write down all the inequality such stuff. So you do not have to figure out by yourself, sit and do it. There's a wonderful algorithm, okay, it's for d-separation. I didn't do that, okay, I didn't because it takes some more time. Yeah, please next. So here are, to end our Bayesian network part, so here are some real life, actual examples. I collected a few of them, there are a lot more nice examples, okay, online. So this is actually somebody built a network. Okay, so Bayesian network to understand in an ICU, when does an alarm go off, or if the alarm goes off, what could have been the cause? There are so many causes, right? So in an ICU, for example, alarm may go off because the ventilator wire would have got twisted, okay, or got disconnected, or maybe somebody pressed by mistake something else. So if you capture all that, this is actually real paper, okay, so this is a research work, okay. So you collect all the stuff and you can analyze all the probabilities and figure out, suppose the alarm went off, what is the probability that the person is under, let's suppose, cardiac distress. Because based on it, the alert should go up. Depend on the severity, the doctor should come in. Or if the cardiac distress, obviously the surgeon has to rush in. Suppose it's only about some, his BP falling down a little bit, 10%, maybe a nurse can come in and fix it. Okay, so these are real life examples. Okay, similarly, that is car insurance. So if a young student applies for a car insurance, what is the chance that actually he is going to get, or should we give the insurance or not, depending on whether he has past history of, okay, how many accidents he has caused, how many cars he owns, and what types of, maybe it's a US example, so it's all cars only. Okay, or how many bikes the person has driven. Okay, how many friends he has and what kinds of circles he do. Maybe nowadays you also see what videos he sees, what Facebook posts he actually posts, how which what do you call, hill he has driven his bike on. Okay, all that is meant now. Okay, so figure out how much insurance you have to charge the person because you want to identify how much risk he is. Okay. Yeah, next. This you cannot see much. Okay, this is our latest example. So just wanted to show that we used it for identifying. If suppose a building construction projects are there, and we want them to be sustainable. Okay, and we want to figure out if you enclose sustainability, what are the likely things that is going to happen to all the phases of the construction. Okay, so I will not be able to cover much, but just wanted to show this is it's not a published, so this is just finished work. Okay. Yeah, so another 5 minutes maybe I'll spend on Markov networks. Yeah, next page. So we have already mentioned this example, okay, and I mentioned we can set up whichever way you want your dependencies, right? Depends on what you understand. For example, I may want to simplest model is the dependence is uniform between every pair. Suppose you have a friend, okay, both of them agree on something is 10. Both of them disagreeing on something is maybe 1 and 0. One person is more likely to agree, another person may be less likely to agree, so maybe 1 and 0. And suppose both of them not agreeing, there is a chance, but it's less. Okay, it's not probabilities, but I have put some weights. Okay, this is how you model. This is a power of actually having Markov networks. You can put in those numbers yourself, depending on what you understand from the actual behavior of the person or behavior of the system. Okay. And then of course you build this of course this is all symmetric in the sense we say that x and y being a or b or b or d or something it's the same, but need not be. In fact, I can have fixed individually relation between a and b I can model separately, relation between a and d I can model separately, c and d, c and b. Okay, there can be 4 such factors which have different numbers, and I can actually build the graphical model, right? So Markov networks are also called Markov random fields. It's an older name and it's used. Okay, so and these are called factors. Okay, and I think some of you will see in the some others talk about factorial models. Okay. So the Markov random field again like Bayesian network. If you have a set of variables x1 to xn, okay, and the probability joint probability is given by product of factors, but there is a normalization factor, right? So normalization term, okay. So that is given by just summing of everything over all possible values that xn takes, right? So now here these factors are there are clusters of factors. They are called cliques. Suppose what is meant by clique is in the graph, okay, a collection of nodes which are completely connected. That means every node is connected to every other node in that subset. Okay, for example, AB is completely connected in this very simple example. Right, these are 4 cliques possible. So I could have taken this, factorization this way. So you identify all the cliques and then you can factorize the probability. Right. The next. There's one example I wanted to give you, real life one, so which touches on machine learning. Okay. So that's why I need, okay, so an additional thing which is called conditional random field. That is Markov network, Markov random field, but for conditional probabilities, not for original joint distribution. Suppose I want to actually do the entire stuff only for p y given x. Okay, not the probability of y comma x. Let's suppose this is a special case, but this special case is useful for us. Okay, so we will, okay, so otherwise it's the same. Only thing is, because y given x, obviously I need to know what x takes value, right? So this is the product, but this depends on, so y given x, but this zx depends on x, because everywhere x is sitting. So that is why this becomes a function of x. That's why it's called partition function. By the way, that's where the word function came from. Okay. The word partition comes from statistical physics. Okay, so you'll not get that. It's all okay. So now with this, next page. So here is a nice example of this in action. Let's suppose you are doing you are building an OCR system. That means optical character recognition system. That means it is a AI machine learning system which is going to recognize the characters from text from scanned images. Okay, you have scanned the picture. So every character is, let's suppose D cross D, let's suppose 16 cross 16 or 8 cross 8 image. Okay, the character, let's suppose for easy case, let's suppose they are all English alphabets for now. Okay. So obviously okay, so what happens, the input would be a sequence of such scanned characters. Okay, so you read the, of course you have to do a lot of image processing to figure out those Q, V and all, but let's suppose you divided nicely and got hold of these. Okay, so this is how they are written. Okay, now human being would have said it should be quest, Quest, right? So let's suppose I want to be able to do that. Now let's suppose I am building a machine learning system for this. What I will do a simplest thing I will do is build a classifier. Given an image, I want to classify whether it has 26 classes. Let's suppose all capital only we are bothered right now. Okay. So, or 128 characters if you want to consider ASCII. Okay. So, I want to decide which of those 128 it is. So, I can build a classifier, right? I can build a neural network. For example, typically CNN, some CNN or something is used to build a network. Given an image, it says Q or V or whatever it is. Okay. Suppose I do that. Okay. Would it have figured out that it is U or it would have figured out it is V? If you don't know anything, I am going to give you images and it has to figure out, you have trained it enough. So most of the time, most likely this would have been V because it would have trained on things which look like V, right? When it is trained, obviously it should recognize it as V, not U. Okay, if it's a good classifier, right? But that doesn't take into account the semantics. That means the relation between the characters. They form words. Okay, words, there are some rules or there are some occurrences in which they get together to form words. For example, this example is taken because the simplest one you can construct, because Q is always followed by U in English. Okay, so if you know that thing, okay, you could have actually figured out. Okay, that's what attention mechanism and all do nowadays. But we don't need to go to that high level of LLMs to actually do this business. If you use a Markov network on top of that, okay, so we can actually construct this, right? Okay, so if you use a Markovian network, so what happens is this was a conditional random field. Okay, so you train a classifier as it is. For example, the output yi should depend on xi. Okay, for example, it will be the CNN or a deep network or whatever. Okay, since characters make up words, yi's are related to each other, as I mentioned. For example, how do you do that? So this is a Markov network for that. Okay. So what we do is we actually learn this Markov network and infer from this Markov network. Okay. So now actually what we do is, so query is given Q, what is the most likely value for this? That's a probability query, right? Probability given evidence I already see in Q. I want to know what is the most probable next. That's a map query. So you run a map query on this. So you're most likely going to get U because you know the joint probabilities. Because you should have learned those joint probabilities from your NLP, natural language processing. Is said Q means probability of Q x given Q is 1 for you and 0 for everybody else. Because of that, my map query will point out U. It will not say, it doesn't, even though V is actually what my classifier gives me, actually this overrides that because of that high level of probability. Like that, actually you can do the map query. That means the characters are not simply read out from the classifier, but the classifier output is given to this Markov network and you run a map query for each character as you go on. Okay, so that's your OCR solution. Okay, which is going to take into advantage of the relation between the letters in a word, in words in English. Okay, so that's how you actually can improve the machine learning. It doesn't matter how much you train your deep neural network is, it will still fail if it doesn't have this additional understanding of what is the relation between characters and words. Okay. Yeah. So okay. So next page. So these are the two main standard textbooks. First one is of course a comprehensive 1,300 pages, really good textbook, a standard book in this field. Okay, Kohler and Friedman. They are Stanford and MIT. So and then Darwish is also he's from UCLA, and this is also a nice book if it's for Bayesian networks. Okay. and he has done a lot of algorithms based. There are a whole lot of books which are all the great books in probabilistic data science have, for example, Mitchell, pattern recognition, Prashad, all have chapters on BCMs. Okay. Maybe the easiest book to read maybe the second one, at least a few chapters. But the first one is comprehensive. You have real complete stuff. Okay. Yeah. Thank you. And any questions or something? We have 5 minutes. Not 15 minutes as well, but 5 minutes at least. Online. Yeah, you don't have questions, so I'll have questions. Go to place slide 13. 1 3. One three. No, after this is. Okay, I'll show you what it is. Okay, go forward. Just see what I do. Okay. You are here, right? Go forward. Forward, 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 forward. Wait, forward. Wait, and this one. So this I asked, but I wanted to ask you again. Okay. Because this is ultimately whatever you models you develop, whatever algorithms you develop, you should relate to what is actually happening also, right? Where it is going to be useful. So I again want to ask the last question. We said that okay, we can do a query and answer questions like whether it is flu or hay fever or not. But what do you think doctor does? Okay, that depends on probabilities. Yeah, okay. So for a doctor, season matters. So based on season, okay, maybe you're a doctor, I don't know, but huh? Okay. So it obviously that boils down to numbers. Okay, so if it is just because there are some numbers, you can have some surprises because they influence each other in such complex ways. Okay, so as you go down, okay, so you cannot easily figure out that stuff. So you can blindly run a map query on it and find out what is the best answer. Okay. Does the doctor do it? Does he or she run a map query? Yes and no. Okay. No in the sense they have not built this network directly, even though they build some kind of such networks, but they have in their mind, okay, season is there, then flu or something is possible, as if these are the symptoms. Some understanding is there, some of them actually draw these networks, not necessarily like this, but some sense. But they don't have the properties directly all the time in their hand. They don't know that flu happens. If this person in Bangalore has a chance of let's say 10% of getting flu in a winter, that numbers also they have some sense. Okay, but roughly 10% chance the person has flu because it's winter season. Yes, change came in. Yeah, it's winter season. Yeah, I can expect flu. You don't say that no, he's having tuberculosis, right? So the first thing is, yeah, there's a good chance it's going to be flu. Okay, so they also use these numbers, and they do definitely do the map query in their head. They ask the what is the most likely cause for this muscle pain. Okay, so it's not very far from how we humans think. Okay, so only thing is it's made into a little more structured way so that it can be run on a machine. Okay, so that I leave it with leave it with that. Okay, and thank you for attending. Okay.
Thank you, sir, for the insightful session and the thought-provoking thought which you left regarding the doctors thing. It was, I want everybody to think on it. Okay. So, like sir said, it's it's not so far that it's not so tough. You can actually do it, but it has to be done in a structured way. Everybody has that understanding. So we shall now break for tea. So we have refreshments arranged outside for you. So we shall get back by 11:40. 11:50. I want all the participants to assemble here. We have the next session. Okay. Thank you, everyone. Thank you once again.
Those who have registered now, order for everyone, key is it. Take it. Next will come on the second front. That's the online session.
Yes, it is. It is. Right, sir. Yeah, that's all. Yeah. Book nice place. What was I think that nothing. Always when I find something, I go and look. No, no, no. That doesn't reach who will be there? Yeah, even because the advantages that would be by the advantages. You have to morning wear business. Concern is also I am going to teach them the upcoming test. So I have to teach them. exam session.
Modeling and its industrial applications using Python by Dr. S. Yadavendra Babu. He is the General Manager and Technical Leader, Global Data Insights and Analytics, Ford Motor Company, Chennai. So Dr. S. Yadavendra Babu is a seasoned data science professional with over 2 decades of academic and industry experience. Currently, he is serving as the General Manager and Technical Leader at Ford Company. He has held multiple leadership roles in analytics and research and development, both in India and in the US. He holds a PhD in statistics from Sri Venkateswara University, Tirupati, and has also worked as a lecturer and a guest faculty at various universities. A SAS certified programmer, Dr. Babu has published and presented research in national and international forums and has delivered more than 50 workshops and 30 FTPs across India. I request you all to warmly welcome Dr. Babu with a round of applause. All of you please welcome. Sir, over to you, sir. You can start the session. So kindly unmute. And others, those who are participants, I request them to please mute their mics. We have some background noise. I request everyone who's joined online to be muted. And I request sir to start the session. Over to you, sir.
Yeah, thank you, madam, for the kind introduction. I request all the participants to go on mute.
Online participants,
I
please
request
be
all the
muted.
participants to go on mute.
I think it's fine now.
Yeah, please go on mute. I am hearing a lot of background noise. Hello.
Sir, I think we can start. They have been muted.
Is it audible? Can someone confirm?
Yes, sir, a bit. You can increase your volume.
Yeah, sure, madam. Okay,
Yeah.
thank you.
Okay, sir. Okay.
Yeah, hi all, good afternoon. Yeah, I am going to talk about the predictive modeling and its industrial applications. The first one is just I will talk about what is statistics and what are all the applications of the statistics and how the statistics will help in the machine learning or artificial intelligence in maybe industry in all other fields. This is one, there are many definitions for the statistics, and this is one of my favorable definition. That is, statistics is defined as the collection of the data, classification of the data, analysis of the data, and interpretation of the results. Why it is my favorable definition is, this is what exactly we will do in the industry. First, we will we have to interpret. When it comes to the predictive modeling, first of all, what is the predictive modeling, right? And how the predictive modeling will help the industry. The predictive modeling is a statistical or the data science technique, and it uses all the statistical methods or the algorithms and the machine learning. What exactly it will do is, it will consider all the historical data and it will create a mathematical model and that mathematical model is used for prediction purpose. That's what exactly the predictive modeling will do. And how it helps organizations make more accurate forecast. And it will reduce the uncertainties and the risk will be reduced. And it will be used in the optimization and it will give more insights from the data and it will be very useful for the decision making. I will give some examples how this will be helpful. The first one is in the predictive modeling, what exactly we have to do is, first we have to define the objective. What is our objective? For what purpose we are going to develop a model, the predictive model, right? First you have to identify the problem. And once you identify the problem, then what you need to do is you have to collect the data. The collection of the data will play a crucial role, right? Garbage in, garbage out. If your data is good, then you will get the more accurate results. That is the data collection part. And then data preparation. Once you collect the data, then you have to do a lot of steps. In academics, the big difference between the academics and the industry is, in academics you will get the simple, the straightforward data, right? But in the industry, it's not like that. Then you have to do a lot of things, right? The cleaning of the data and many things you have to do. I will explain in the coming slides what exactly we will do. And then the model selection, and based on the data and based on your objective and what kind of the data you are having and what kind of model you have to develop, right? And based on the data and the objective, we have to identify the model. Whether it is a regression model or logistic regression model or XGBoost or cluster analysis or fact, whatever it may be, the methodology. I am not going to talk about that one now. The model selection, that is the next step. Once the model is selected, what exactly we will do in the industry is some percent of the data is used for developing a model and the remaining portion of the data is used to test the model, whether the model is performing or not. In general, 70-30 or 80-20 or 60-40, that's what exactly we will do. For example, in the 70-30 case, 70% of the data is used for the model development and the remaining 30% of the data is used to validate the model, whether the model is performing as expected or not. That's the test of the model. And once the training and the testing is done, then do we need to change anything? Right? Do we need to do any adjustments? That comes under the hyperparameter tuning. And once the hyperparameter tuning is done, and once you decide the model is good, then what you can do is you can deploy and use the model. And here, as I mentioned, the difference between the academics and the industry is, in the academics you will get the straightforward data. And for example, a linear regression model, you fit a linear regression model for the given data and estimate the number for a so and so number, right? Then you will develop a model and you will estimate the number and you will submit that one to your professor and your professor will give you the marks. That's it. That's over. But in the industry, we will collect the data and we will develop a model and the model is going to deploy. For example, if the model is approved and we are going to deploy the model and from next day onwards, we will test whether the model is performing as expected or not. For example, if I am expecting, maybe I can give some numbers to my business team. Okay, from next month, we can expect 100 defaults. And in reality, if it is 110 or 120 or 90 or 80, that means the model is performing as expected. I am saying we can expect 100 defaults and in reality, there may be 500 defaults. That means my model is not performing, right? Then the question will come, hey, you mentioned this many defaults we can expect, but it is completely different. Your model is not performing. Then I have to look into the details and what happened and why it is happening. All these things we need to look into. And what kind of the predictive modeling techniques available? Right, the first one is the regression models we can use. If your dependent variable is continuous variable, then you can use the regression model. For example, the sales forecasting, inventory levels, for these kind of problems, you can apply the regression model. And the second category is the classification model. For example, success, failure, right? Yes or no, for churn or non-churn, fraudulent or non-fraudulent. For these kind of the categorical problems, you can apply the classification models. Under the classification models, there are many techniques are there. You can use the logistic regression, decision tree, random forest, support vector mission, XGBoost, and any model you can apply for the classification techniques. And the next category is the time series model. If your data is depends on the time over a period of time, right? Then you have to apply the time series model. For example, the weather forecast, sales projections, and all these things. And why we have to use the time series models? It depends on the over a period, it will change over a period of time. That means you have to look into the trend, what is the trend, and what is the seasonality, what is the cyclical factors are affecting, right? All these things you need to look into when it is a time series model. And the other one is the clustering techniques. The clustering techniques is nothing but you have a set of observations and you have to group them based on their characteristics. Right? That's the cluster analysis. Why I am keeping the cluster analysis under the predictive model, I can talk about later. And the neural networks, and if you have maybe the complex patterns, right? And then you can use the neural networks. And nowadays we are using the ensemble method. The ensemble random forest, boosting, stacking, and all these models comes under the ensemble methods. How the ensemble method will do is, it will take a sample of observations. See, for example, the difference between the logistic regression and ensemble method is, for example, you have 100 observations. And as I mentioned, 70% of the data is used for the development. That means 70 records are used for the development and the remaining 30 are used for the testing purpose. Here also the same thing, you are considering the same 70 observations. In logistic regression, it will consider the entire data and it will come up with a single model. Whereas in ensemble method, it will take a sample, a random sample out of 70, and it will come up with a model. And again, it will take another sample, third sample, fourth sample, and then based on the average, or based on the success, or based on the tick marks, right? And it will ensemble. That's the reason we are ensembling different models. That's the reason we are calling it as ensemble methods. And where we can use this predictive modeling? In the finance, the risk assessment or the credit worthiness of or the loan default, for these kind of things we can apply the predictive modeling. For example, if you are going to a bank, right, what the banks will do is they will collect all the information from you and they will assess your risk score. The risk score may be 0 to 100. If your score will be the probability of payment score, it's called POP score. If the POP score is good, then they will approve the loan immediately. If the POP score is very low, they will reject your loan. If the POP score is in between, then what the banks will do is, if you are requesting for a 10 lakhs loan, they will reduce the loan amount. They may issue only 5 lakhs. Sometimes we don't know. Yeah, I requested for 10 lakhs loan and the bank is giving only 5 lakhs. Why they are giving 5 lakhs? That means the risk score is in moderate. That's the reason they are reducing the loan amount. Or sometimes what they will do is they will ask to bring maybe the co-buyer or some surety, government employee surety. These kind of things will happen. All these things, the background is the predictive modeling. The predictive modeling will generate the score, and based on the score, the banks will take the decision. And the next one is the healthcare. In the healthcare also we can use the predictive modeling for the disease prediction, right? And identify whether the patient is under high risk or low risk, right? And there are many things we can use by using the predictive modeling. And in the marketing, right? You may be request, for example, you are running a company and you want to give maybe maybe the cards, right? Bonus cards to few customers. And how do you identify the customers? And what basis you will identify the customer, right? And how do you segment the customers? That one is the customer segmentation we can use. And the predicted customer churn. For example, if you are using Zio or Airtel network, whether the customer is going to continue or not, that one comes under the predictive modeling. And forecasting, right? All those things I am not going into the details. And the supply chain management. the the logistics operations from where to, there may be different places you have the go downs and they have to transport, right? And all the logistic operations, how to manage, that one also comes under the predictive modeling. And the insurance, the predictive modeling will play a crucial role in the predictive modeling, in the insurance, right? And to maybe identify the risk of the policy holder, right? And based on the risk, the premium amount will increase, right? And if it is a low risk, the premium amount will be very low. Yeah, maybe you can check the simple thing, right? For example, if you are taking the insurance for a 20-year the child, maybe 20-year boy and maybe 70-year guy, right? And you can see the insurance premium will be very high for the old age persons. Why? It is the based on the risk. How they will identify the risk? It's based on the predictive modeling. And the weather forecast and the urban planning and the manufacturing, right? When the engine is going to maintenance, right? And for example, even if you are purchasing AC, right, or washing machine, and they will give you the warranty, 3 years, 5 years. For some products, they will give only 1 year warranty. For some products, they will give 5 years, 3 years, 10 years. On what basis they will give? Again, they will use the predictive modeling. And most of you are the engineering students, right? And that's where we can use in engineering, right? And for the predictive maintenance, we can use. For example, the sensors will collect all the information and how to use the data, right? And the predictive engineering analytics for the designing purpose. If you are designing some of the product, then what kind of the data is required and all those things comes under the predictive modeling. And the process optimization. If there is any process and how to optimize or how to improve the process, that one also comes under the predictive modeling. And the quality, right? To identify or to produce the quality products, right? For that purpose also, we have to use the predictive quality. And the failure prediction, when the model is going to failure, or if the bank is giving a loan and when the customer is going to default, right? That is the failure. The failure prediction purpose also, we can use the predictive modeling. And in the software engineering also, we can use to identify or to predict the defects, which will, and where we can improve the quality. For that purpose also, we can use the predictive modeling. And there are many other cases we can use the predictive modeling. And as I mentioned, in the predictive modeling, there are different steps. The data mapping is the first step. The data mapping, as I mentioned, the data will be coming from different sources. And you have to combine, for example, in the banking data, take the loan data, right? And let us consider two customers. And one customer has taken loan in 2023 and the other customer has taken loan in 2025. And if you look into the first customer, every month he will be paying EMI. He has taken the loan in 2023, right? 23, 24 and 24 months and plus 10 months, almost 34 months, 34 EMIs he has paid. That means for under his name, 34 records will be there. Whereas the second customer, he has taken loan in 2025. That means under his name, there may be only the 10 records. And how to maybe segregate this one, right? And for each customer, you have to make it as a single row. That is, comes under the data mapping. And the data creation, also sometimes what we will do is, we will create new variables based on their income. What is their average income, or what is the minimum income, what is the maximum income, what is the minimum loan amount, what is the maximum loan amount, what is the average loan amount, right? And you have to segregate the loans also, right? And the loans also, for example, you have the personal loan and you have the vehicle loan, right? And all these things, how do you manage? That one also comes under the data creation. Once that is done, then you need to look into the exploratory data analysis. Exploratory data analysis will play a crucial role in any modeling techniques, right? For each and every variable we can look into. There may be hundreds of variables, and each and every variable we can look into. What is this variable? For example, let us take age. And age, for example, it's a banking data. And the age, generally what we will think 0 to 100 will be the reasonable age for any human being. And for example, the customer's age is 2 years. Is it make sense? It does not make sense because for a 2 years kid, the banks, they may not issue the loans. It may be instead of entering 25 or 52 or something, it's a wrong entry, it's a merit as 2, right? And these kind of issues will be there. And for all these things, you have to address under the exploratory data analysis. And sometimes, maybe we don't have any data. That means the data may not be collected. In such cases, and how to handle all those things comes under exploratory data analysis. And then the variable creation, as I mentioned, we have to create some variables, and the variable transformation also we have to do. For example, maybe if you have a variable age and income, the age variable, as I mentioned, it ranges from 0 to 100, and the income variable, it's a 0 to millions, right? And you cannot compare, right? It's not apple to apple comparison. That one, what you need to do, you have to transform the variable. And the variable selection, there may be hundreds of variables, and the basic difference between the statistical technique, for example, you can take the logistic regression as a statistical technique, and the machine learning technique as XGBoost, you can consider. The variable selection, it plays a crucial role in the statistical modeling. Because and in the logistic regression model, you will keep only 10 to 15 variables in the final model. Whereas in the XGBoost, you can keep hundreds of variables. But why we have to? Right? And you can ask the question, okay, if the logistic regression is restricted only 10 to 15 variables, then why I have to use the logistic regression? Why can't I go for the XGBoost or some other machine learning model? Right? There are some restrictions, and you cannot rely on the machine learning model completely because you are using hundreds of variables and you don't know what is happening. If the small change in one variable, it may impact the model and you cannot explain for what reason there is a change in the model. If you have limited number of variables and if there is a change in the model and you can explain because of this particular variable there is a change in the model. Maybe if you take in the banking industry, not in maybe in India, but if you look into the North America or European countries, US, Canada and Europe countries, and if the bank, if you are applying for a loan and if your loan is rejected, then the customer has every right to know on what basis they rejected the loan. Here we don't bother. When we apply the loan, if the bank is rejecting our loan application, we don't bother and we will go to the other bank. But in US, Canada and Europe countries, what they will do is they will go to the bank and they will question on what basis you rejected my application. They have to explain. This is because of this score is low, this score is low, or maybe these are all the factors maybe affecting your the score, and that's the reason we are rejecting your application. If we have 10 variables, it is easy to explain. If we have hundreds of variables, you cannot explain. That's the drawback of the machine learning. And the multicollinearity check, this multicollinearity, if you are using the statistical model, then you have to check the multicollinearity. If it is a machine learning model, no need to go for the multicollinearity. And the modeling, as I mentioned, you have to develop a model, and once the model is developed, then you have to test whether the model is performing as expected or not. And then you have to validate the model. The validation, how we will do is, for example, if you are considering the data up to, maybe for example, I am taking the 10 years data, right? And I want to develop a model. What I will do is, I will consider, maybe I have the data till October, let us say, October 2025. What I can do is, I don't consider the data from Jan to October in my model development. What I will do is, I will use the data till end of December 2024. And I will follow the 70-30 rule. 70% of the data I use it for the model development and the remaining 30% for the validation, the testing. And what I will do is, this data is not at all involved in any of this, right? I am considering this data is completely independent. And I will test whether the model is able to perform in the independent sample also. That's what we will do under the model validation. In the model development, if it is a success, and the model testing also success, and the model validation also success, then we will go for the implementation. We will communicate the results or business insights to the business team, and we will go for the implementation. This is what exactly we will follow when we are developing a model. And coming to the regression methods, And I'm not going into the details of the regression methods, just I will give you the glimpse of what the methodology is. For example, here I have two variables. One is the house size and the second one is the selling price. And these are all the different data points I am having. Now I want to draw a regression line. Maybe I can draw this line, or maybe I can draw this line also, right? Or I can draw this line also. And which one is the correct one? And how do you decide which one is the best line, right? For this what exactly the linear regression will do is, it will calculate the difference between the line and the actual data point. And it will, this is the another point, and it is calculating again the difference between the line and the data point. And what exactly it will do is, it will sum it up. For example, here let us say this number is 10, the line, on the line the point is 10. And let us say this is 20, and let us say maybe this is, okay, here you can see the point is it's 65 around here, and here is 120, and this point is 80. Now what we can do is, this is, if you take the difference between these two, here you will get the positive number. If you take difference between these two, you will get the negative number. And if you sum it up, some negatives and positive, it will minimize. That's the reason what we will do is, we will take the square of the differences. Here take the square and here take the square. Why we have to take the square is, for example, let us take 10 is the point here. Let us assume this point is 10 and this point above point is 15 and below point is 5. Now the difference between the above point and the line is 5, and the point and this one, the below point, is minus 5. Positive 5 plus negative 5, that will be 0. The interpretation will be, there is no difference between the line and the data points. Is it true? No. There is a difference. That's the reason what we will do is, if you square the difference, then 5 square will become 25, and a negative 5 square also it will become 25. 25 plus 25, that will become 50. That's what exactly it will do. In the logistic regression, so we will use the method of least squares. What it will do is, for example, this line, it will calculate all the squares. And for the second line also, it will calculate all the squares. Third one, it will calculate all the squares. And wherever it is a minimum, that will be the final regression line. That's what exactly the linear regression will do. I am not going into the formulas and derivatives, all those things I am not going into the details. This is the way the linear regression will work. And how the decision tree will work? For example, if you want to buy a car, and if the color is red, yes, and you are interested to buy a red car, and if it is yes, then you are looking into the model and which model it is. If the model is maybe after 2010, then you can buy. And if the model is prior to 2010, then you are looking into the mileage. If the mileage is less than 50,000 kilometers, then you want to buy, or otherwise, if the mileage is greater than 50,000 kilometers, you don't want to buy. And if the color is not red, and then what alternatives you are looking for? You are looking for yellow. And if it is yellow, then you are looking into the make, what vehicle make it is. If it is Ferrari, then you are going to buy. If it is not a Ferrari, then you are not going to buy. If the color is not yellow, then you are not going to buy. This is the way the decision tree will work. And how the random forest will work? As I mentioned, this is our training data set. Let us say the 70% of the data I mentioned, right? This is the 70% of the data, the training data set. What it will do is, it will take a sample. This is one sample and this is the another sample. And in the first sample, it is considering the first sample and it is developing a tree. And it is taking the second sample, developing a tree, and so on. Now, what it will do is, this is the tree 1, tree 2, tree 3, and so on, tree n. Now, based on the majority vote, it will decide. This is the way the random forest will work. Now, when it comes to the classification methods, how the classification methods will work? This is the logistic regression. In the linear regression, you have the straight line. But in the logistic regression, it will be the curve, right? This is the curve we are going to maybe estimate, and the probability values ranges from 0 to 1. If you have higher score, then it is good to go. If it is a lower score, then it is not going to happen. And the support vector mission, and here also the same thing. This is the center line. That will be, this will be the maximum margin hyperplane, and the right side one is the positive hyperplane, and the left side is the negative hyperplane. It is this center line, how the center line will divide the grain and these points, right? That's what exactly this will do. The support vector mission will do. And the k neighbors, nearest neighbor algorithm, and here you have a group of data, and here also this is one category and this is the another category, and this is the new point. Do you want to keep the new point under category A or category B? And what it will do is it will identify, right, and where it should fall. And for example, in this example, it is close to the category A. That's the reason it is keeping under category A. I will go through, I will share you some of the examples. And the clustering method, and what the clustering method will do is, you have the data. This is the data you are having, and you decided to keep 3 clusters. And what it will do is, this is one, red is one of the point, and the green is one of the point, and the blue one is another point randomly generated. And now what it will do is, it will use the k-means algorithm, and these two are falling in one category, and all these points are calling another category, and these blue points are calling falling under the third category. Now again what it will do is, it will calculate the mean, the round, the circle. These are all the average points, mean points. Now again what it will do is, based on the average value, again it will calculate the difference, right? And it will again rearrange. And then again it will calculate the average. Again it will calculate the difference. And finally, this is, it is generating 3 clusters, and these 3 points fall under one cluster, and this falls under the second cluster, and this falls under the third cluster. This is the way the clustering methodology will work. Now, I'm not going into these things. Maybe I will show you some of the real-time examples and how you have to do. Can someone confirm, are you able to see the Python code?
Yes, yes.
Can someone please confirm?
Yeah.
Are you able to see my Python code?
Can you ask him to increase it? There are just your mic is there on mute. Tell him to increase font.
Sir, we are able to see, but can you increase the font size a bit?
Yeah, sure. Yeah, I can do that.
Ah, yes. Yes, yes.
Oh, yes, sir, it is visible, sir.
Okay, okay. Okay, first let me talk about the linear regression model. And I am using the NumPy package and the pandas and the matplotlib library and the Seaborn. These are all the libraries I am using for the linear regression model. And if you have the data, then what you can do is,
Message.
Yeah, is it audible now?
Yes, sir. Audible.
Okay, okay, thank you. Thank you. Yeah, here what I am doing is I am considering two variables for the linear regression model, and my independent variable is number of hours studied, and the dependent variable is my final exam score. And here what I am going to do is I want to simulate the data. Here I am going to generate 100 observations. This np.random.rand and 100 I am giving. It will generate 100 observations. And here I am using np.random.rand. That means it will use a uniform distribution. That means the minimum number will be 0 and the maximum number will be 1. The numbers, it will lies between 0 to 1. And times 10. That means I am multiplying with 10. That means my minimum number will be 0 and maximum number will be 10. 100 students and the number of hours studied is 0 to 10. That's what I am going to generate here. And to generate my dependent variable, I am assuming the relationship. The relationship is the exam score equals to 50 plus 4 times the number of hours studied and plus some noise. And 50, this is the basic score. That means the minimum score the student will get. And based on the number of hours, and for each hour, he will get 4 marks. That means if the candidate is studying 10 hours, that means 4 into 10, 40. That means 50 plus 40, 90. And then plus some noise. And I have to add some noise. Why we have to add some noise is, for example, if consider two students, and both the students studied 10 hours, exactly 10 hours. Will both the students will get the same marks? No. And there are different other factors we are not considering, right? The other factors where the student's prior knowledge and what is the natural ability, what is his anxiety and the quality of the study and quality of the sleep in the night, right? There are many other factors. We are not considering all the other factors. That's the reason we are adding noise. Now, here I am generating my dependent variable. The final exam score equals to 50 plus 4 times the number of hours studied and plus here I am generating, again this is the random.rand n. Here this is the difference. If you are using the rand, it will generate uniform distribution, and if you are using rand n, it will use the normal distribution. Why I am using normal distribution? Normal distribution means it will consider the up and downs, right? But here it is only one side, and here positive and the negative also I need to consider. That's the reason I am using the normal distribution 100 times 5. That means it will add or subtract 5 marks. That is the noise. And now I have my dependent variable. Now I have my independent variable. Now here what I am going to do is, for the visualization purpose, and I am creating the data frame. And in the data frame, and by using this data frame, I am going to use the visualization, the x-axis and y-axis, how my data looks like. And for the visualization purpose, I am using the scatter plot. And on x-axis, I am plotting number of hours studied. On y-axis, I am using the final exam score. And the title, the number of hours studied versus the final exam score. And the labels and all those things. This is for the scatter plot purpose. And now, as I mentioned, what I have to do is, I have to maybe divide the data into two pieces, right? As I mentioned, one is for the training purpose and the other one is for testing purpose. Here, X train, X test, Y train and Y test I am doing. And here the split what I am doing is the test size is 0.2. That's what I am doing here. That means 20% of the data I am using for testing purpose, and the remaining 80% of the data is using for the modeling purpose. And how I am using, I am randomly selecting these records, the 80% or 20% of the records. And here again, why I am keeping this number is, that is the random seed to generate the same number of the same observations next time. Next, I am printing here what is the training size and what is the test size and what kind of model I am going to use here, the linear regression model I am going to use. And the model fit is based on the testing data. And once the model is done, then I need to look into how my model is performing, right? And for that purpose, I am using the mean square error and then R square value I am using, and then I am going to visualize the regression line. In the beginning, just I am using the scatter plot, and now I am going to visualize the regression line along with the regression equation, and after that, I want to maybe identify or I want to predict if the number of hours studied is 7.5, then what will be the score? This is what exactly we are going to look into this one. Just let me run this code. This is the initial data. As I mentioned, this is the scatter plot, number of hours studied versus the final exam score, and this is the title, and this is, and the next one is I am generating another one, right, with the regression line. This is my regression line, and this is the regression equation, y equals to 3.80x plus 50.71. This is my regression equation. And then even if you look into here, what is the score? Okay, this is my sample data. It looks like the number of hours studied and the final exam score. And the data shape is, I have the 100 records and 2 columns. And as I mentioned, I am considering 80% of the data. That means 80 samples for training and 20 samples for testing. And then this is the model coefficient. As I mentioned, its intercept is 50.71 and this one is 3.80. We have seen this in the chart. And this is my sample predictions for the 5 records. I am taking the actuals versus predicted values. And I am calculating the mean square error. The mean square error is 16.34. If the mean square error is low, then the model is performing good. And R square is 0.89. That means 80%, 89% of the variation is captured, right, or explained. Right? This is a good model. Out of 100%, it's close to 90%. It is able to predict. And this is the way we can develop a model and then we can interpret. This is about the linear regression model. Next, let me pick maybe some other model. Maybe let me pick the logistic regression example. Here the logistic regression model, when we have to use the logistic regression, it's a classification problem, right? Then if it is a binary case, then you have to use logistic regression model. Here what I am going to do is, here also I am generating the data. Here how I am generating the data? There are 3 variables. My target variable is admitted or not admitted. That is my dependent variable. And my independent variables are 2 variables. One is based on the exam score 1 and exam score 2. There are 2 exams, exam 1 and exam 2. And based on the exam scores, whether the student admitted or not admitted. That's what we are planning to do here. And here, now, What I am going to do is, I am going to generate 100 records for not admitted students. 100 not admitted students, I am going to generate the data. And if it is not admitted, that means the student's score will be very low. Here I am taking 50, that is the average score. And for the maybe if you want to use the normal distribution, then you have to mention mean and the standard deviation. Here mean is 50 and the standard deviation is 10. That's what I am considering in the exam 1 score. And exam 2 score, it's a little bit I am increasing the marks, average marks, that is 55. And the variation is same, I am considering the standard deviation 10. And all the students are not admitted, right? That's the reason the y variable, I am keeping all the zeros for this. And for admitted students, I am considering 100 records, 100 students. Here for admitted students means the students got very good score, and here in first exam it's a 75 marks, and the second exam the average score is 80 marks, and admitted, that means I am keeping all the ones. Now I have 3 columns. The first column is my dependent variable, it's a zeros and ones, 100 zeros and 100 ones. And my first column is exam 1 score. Exam 1 score in the previous one is 100 and this one is 100, 200 records, and exam score 2 score also 100 plus 100, 200. Now what I am going to do is I am combining the entire data. Now my data is having 3 columns and 200 rows. And here also I am going to do the same thing, the training and the testing. And here X train, X test, Y train, Y test, and all those things. Here I am using the test size 30. In the linear regression model, I used 0.2. That means I used 20% of the data for my testing purpose. And here I am using 30% of the data. Now I am using the logistic regression model here. And in the logistic regression model, and how to predict, here I am predicting the scores for each and every record. And then the accuracy, how we will calculate the accuracy is predicted values versus the actual values. That's the way we will calculate the accuracy. And then we will calculate the confusion matrix. Confusion matrix is nothing but a 2 by 2 matrix. And then the precision and recall I am calculating. And then I am plotting all these points. And then the finally the addition boundary, what is the exam score and what is exam 2 score and all those things I am going to maybe evaluate. Okay, let me run this part. Hello.
No, sorry, it is audible.
Okay, do you want to stop or something happened?
You can continue.
Okay, let me complete this example. Okay. Yeah, here it took some time to generate the data and everything, right? Now this is my sample data. See, this is the the result. These are all the scores of the 200 students. The red one is not admitted and the blue one is admitted. And this is the logistic regression is going to draw a line to divide the entire points, all the points into 2 categories. This is what exactly it will be doing. Maybe you can observe here the red one is falling under other side of the line, and this point also falling on the other side of the line, right? That means this is a wrong prediction. The model is not able to predict exactly. That's what is happening. Yeah, we will see how it looks like. And here the same thing, the data shape, and here the training and the testing and all those things. When it comes to the data, this is the data. The total 200 records, out of 200, 70% of the data is used for training, and 30% of the data is used for testing. And these are my first 10 actual values, 0, 0, 0, 1, 1, 1, and so on. And these are all my first 10 predicted values. And model evaluation accuracy, 97% it's exactly predicting. And how to calculate the 97%? See, in the test data, we have 60 records. And out of this one, the 29 exactly predicting, here also 29 exactly predicting, and these two is wrongly predicted. That means 58 divided by 60, that is the accuracy. And the precision and recall, F1 score, and all these things to support how our model is performing. That's the reason we will use all these things. I am not going into the details of these things. Now, how the prediction will happen? Just I will run the another piece of code just to show you how the prediction will work, and then I will stop. And I am using the same data, and I am adding some additional information here. That's the only thing, the difference between the earlier one and this one. Here I am adding few students, five more students data, 55 and 60, these are all the scores for the first student, and 80 and 78 second student, and for third student 65 and 70, and so on. If you look into the score of the first student, 55 and 60, it's a very low score, and generally it's not admitted. That's what our thinking, right? But we don't know what the model says. And the student 2, 80 and 78, it's a good score, right? Maybe likely admitted. And 65 and 70, it's a moderate score, and we don't know, we are not sure whether the student will get admission or not. Score, that means definitely the fifth student will get the admission. That's what our intuition, right? Let me run the code, and we will see what the model says. Yeah, just look into this one. This is the earlier one. Now we are adding few more, right, points. 1, 2, 3, 4, 5, right? These are all the green dots are the new students. Student 1, as we expected, not admitted. Student 2 is admitted. Student 3 is admitted. Student 4 not admitted. And student 5 is admitted. This is the way the logistic regression will help. Based on the previous or historical data, it will generate a model, and it will apply that model for to evaluate new students or to evaluate new customers, right? And based on the probability value, it will decide whether it will go on the right side or left side, right? That's the way the logistic regression will work. And this is the classification problem. Yeah, it's time 1:05. Maybe I can stop here. Any questions?
So there is no questions.
Okay, thank you.
Just 2 minutes can summarize.
In the same way, you can use, right, the many things. This is one of the classification problem. And the other thing is, maybe it's already 106. I thought of showing one of the cluster analysis. If you are using the k-means clustering, what exactly it will do is, the k-means clustering, it will calculate based on the means, and then it will come up with a solution. But if you are using the probabilities, right, then you may get completely different kinds of results. And these are all maybe when you are using the traditional methods and when you are using the machine learning methods, that's the big difference. Now, because of the AI or because of the chatbots, right, and even the learning, it became very easy, right? No need to depend on any your professors or someone, right? And you can use the LLM or you can use a chatbot. Hey, can you provide some information on the cluster analysis? Or can you provide some information on the factor analysis, right? It will provide all the required information, but you have to spend time and you have to understand what exactly it is doing and how we have to interpret. Once the model is developed, the interpretation will play a crucial role, right? For example, just I will conclude with simple example. For example, in the banking example, for a customer, the bank generated a score. That is the POP score, probability of the payment score. Let us assume the probability of payment score is 0.9. That means the probability value is 0.9. That means there is a 90% of the chances that the customer will pay back the loan. That means his score is very good and the bank will approve the loan. But generally, when you are working in an industry and you will be dealing with different kinds of the customers. And if you are talking with, for example, I have developed a regression model and I want to explain this model to a statistician and he can understand, okay, the probability score is 0.9, it is a very good score and maybe we can go ahead with the loan. And if you are explaining this one to a business person and he will ask, yeah, I don't understand. Yeah, you have developed a very robust model. It's a very good model, logistic regression model, but I don't know how to interpret the score. And what is the meaning of 0.9? The customer will pay only 90% of the loan amount? Or how to interpret, right? That kind of the questions will come. Maybe how do you interpret that 90% of the score? That's not the meaning of the 90% of the score. The score is 0.9 or 90%. That means the customer is going to pay only 90%. That's not the assumption or that's not the interpretation. What you need to do is, for example, if there are 100 customers, similar customers, and what you need to do is you have to group them, all the 100 customers into one group and take the average. The average is 0.9. That means out of these 100 customers, 90% of the customers are going to pay. The interpretation is completely going to be in other way, right? And for each customer, you cannot interpret, he will pay 90% of the loan amount. But if you are considering 100 records and 100 customers, out of 100, we can expect 10% of the defaults or 90% of the customers will pay back the loan. Then it is easy to convince the business people. And not only developing the model, the interpretation will play a crucial role. Whatever the work you are doing, right? And whatever you are learning and how you are presenting, that the presentation is more important. Yeah, I will maybe stop here.
Hello. Yes. Thank you, sir, for sharing such invaluable industrial insights and applications of predictive modeling. I request everyone to please give a round of applause for sir. So with this, we shall conclude the session and we will break for lunch. Okay, so gather your bag after lunch. We have two more sessions lined up in afternoon. The first session will be handled by Dr. Jyoti AP, that is on machine learning models based on statistics. And the second session, that is after the tea break in the afternoon, it will be handled by Dr. Subramanya T, the foundational logic behind big data analytics. So we shall break now. Once again, thank you, sir, for your contribution and sharing your insights.
Yeah, thank you, madam. Thank you. Thank you very much.
We shall break for lunch now.
You can log out, sir.
Okay. So you finish your lunch and you come back by 2 to 5 like that we start. By 2 5 like that we can come back.
Good afternoon. Welcome back. Our next session is on machine learning algorithms based on statistics by Dr. Jyoti AP. Dr. Jyoti AP is an accomplished academic and researcher currently serving as associate professor and head of mathematics and computing program in the Department of Computer Science and Engineering at MS Ramaiah University of Applied Science, Bengaluru. A postdoctoral research fellow from Shinawatra University, Thailand, Dr. Jyoti AP is a senior IEEE member and actively contributes as a part of IEEE Executive Committee of the RUA student branch. With over 18 years of academic and R&D experience, her expertise spans communication systems, wireless sensor networks, IoT-enabled intelligent infrastructures, and AI-driven network optimization. Her research has focused on energy efficient communication protocols, smart city frameworks, and healthcare communication systems. Dr. Jyoti AP has published 40 plus Scopus Index papers, authored books and book chapters, and holds multiple international patents. She has also received funded research projects, mentored students for IEEE competitions, served as a technical program committee member, keynote speaker, and reviewer. A recipient of several awards, including the IEEE Outstanding Achievement Award and Research Excellence Awards, Dr. Jyoti AP is also known for her contributions as a resource person for ISRO scientist training programs and for her leadership in promoting innovation, research, and mentorship in the field of next generation communication technologies. Dr. Jyoti AP will cover the fundamental principles of machine learning, including model training, evaluation, and applications that shape today's intelligent system. So let's welcome Dr. Jyoti AP with a big round of applause. Thank you.
Good afternoon all. So after lunch, I hope you are all will be awake actually to listen to this talk. So I just want to give a brief about the machine learning algorithms. Given 1 hour of time, I will try as much as possible to cover at least one model in depth with respect to mathematics and how it is statistics is being used in machine learning and all that stuff. Okay, so I'll just try to convince you with at least one algorithm. At least if you learn one algorithm today, that is at least helpful to you in some way. At least the basics we have to start from. So as all of us know, like statistics basically based on hypothesis. Okay, so we do they do the data collection, do some hypothesis testing, and we come up with the results. But in machine learning, what happens is, am I audible?
Yes.
But in machine learning, what happens is we will actually train our model depending on the some data set will be there, so which will have all your data. So what we try to do is first we will train the model with the available input and output that is there as part of your data set. Okay. So after training your model, we'll give a new data to it that is called as a test data. Okay, so depending on the trained whatever the things outputs it has got, so based on that your ML model should be able to give you a output which is giving a actual result of your test data. Okay, so for example, if your mother is actually teaching a kid means one apple means she will tell this is red in color, apple is red in color, round in shape and all that stuff. So the same way you will try to actually model your machine learning model with respect to training data set. Okay, so whatever the data set is there, we will actually divide it into training and testing part. We actually model the machine with respect to the training data set, and then we test with the test data set. Hope this part is clear to everyone. Okay, so this is the basics of machine learning and how it is different from the statistics. Okay, so there are few terminologies which you need to understand when it comes to ML models. So model is actually the representation of your model which you are developing, and then it comes the features. For example, I told you apple now. Apple has some color, red color. So it is one of the feature of that particular thing that we have taken into consideration. Target is your output, that is a predicted value from your model, and training is, as I told, Training is basically the input features, whatever you are providing to your machine. And predictions is the output, what you make out of the test thing. Okay, so these are the few terminologies that you need to understand. Next. So there are three types of machine learning. One is supervised, unsupervised, and semi-supervised. Supervised basically will have a labeled data set. Say for example, if you want to know whether you are attending today's program or not. So if we give a poll to you, somebody will say yes, somebody will say no. So in order to find out how many will attend, how many will not attend, we can just float a poll to you. So you might say 1 or 0, right? So depending on it, like only two things are there. So that means yes or no. So such kind of things I have given as an example over here. So user ID, gender, age, salary along with the purchase. So purchase, whether the client is doing the purchase or not. 0 means no purchase, 1 means there is a purchase. So you are trying to label your data. If there is a purchase, you put it as 0, otherwise you put it as a 1. So that you are actually finding out in the later stage when you are doing the prediction whether the client will do the purchase or not. Okay. So that's how you try to label your data in your supervised learning model. Okay. So unsupervised learning model, there will be no labels as such. The machine has to learn by itself and do the things. There are different kinds of ML models with respect to supervised, unsupervised and semi-supervised also. Semi-supervised is combination of both. Okay. With label and without label, you will have the things. So here with the supervised learning, you will have classification and regression. So just now I told you about the classification, that means 0 or 1. Binary classification you can say. Why do you call it as binary? Because 0 and 1 only. Two values are there, you call it as a binary classification. So that is the example over here. Regression means when you see this, it is a continuous value. It is not a discrete value. Discrete value means either 0 or 1. But here you have a continuous value. So if you want to get some classification or regression with respect to your supervised learning, you have to have a continuous value for your regression and either binary, some kind of classification for your classification models. So coming to the types of supervised learning, just now I explained you the classification and regression. So examples of supervised machine learning models: linear regression, nearest neighbor, Gaussian naive-Bayes, decision tree, support vector machine, random forest. There are a number of algorithms available. Since we have basic students over here who doesn't know the basics of ML as such, so I am keeping it little basic. From the basic we'll start and finish at least one model for your reference. So as we can say, very much relevant to your statistics, you will have a linear regression and also your logistic regression. So in detail we will see few of them along with SVM and other things as well, but I will not be able to cover much on the clustering and other stuffs today because only 1 hour time is. So with respect to unsupervised learning, we have k-means clustering. So clustering means what? This is one cluster, this is one cluster, right? So we try to group the particular data points with respect to how much nearby they are, or on any other parameters we will try to group it. So that is called as clustering basically. So one more thing is there which is called as a association rule. Association rule based is a prior algorithm. We are not going in depth with the unsupervised as on today. So semi-supervised, as I told, you will have a labeled data. You will train the model with the labeled data. You will also have the unlabeled data along with the labeled data. So you use this to train your model to predict the labels for the unlabeled data. So once you get it, you use both your pseudo-labeled. Pseudo-labeled data is nothing but whatever you are giving it. Okay. So those things are called as pseudo-labeled data. So both you use finally to get your model output. So this is called as semi-supervised machine learning. So as I told, labeled and unlabeled. So you have only labeled data, then it is called supervised learning. You have semi-supervised learning wherein both labeled and unlabeled data would be a mix. So as I told, labeled data will be used to train your model first, and then you try to predict your or label your unlabeled data, and then you call it as a pseudo label, and both you use again to predict your model. This is the thing used in semi-supervised. So in regression, it is actually a statistical measurement used in finance, investing and other disciplines. wherein as I told it is a continuous value. So there will be a independent variable, there will be a dependent variable. So as I told you in the example, I told you about the purchase or something, I told for the classification. Again in the regression also I told you there are some profits, losses, something like that. Related to finance, you can have some example for your regression model. So in regression also you have many types. One is linear regression, and again in that you have simple linear regression, multiple linear regression, polynomial regression, decision tree regression, random forest regression. So many different types of regressions are available. So we will start with the first one, that is simple linear regression. So simple linear regression is very much easy to follow. All of you know a straight line, right? What is the equation for the straight line? Y is equal to mx plus c. That is a basic thing all everybody will know. So here simple linear regression is also having this similar line only, and this line you are representing is similar to y is equal to mx plus c. Are you getting it? So it is represented as constants b0 and b1. Okay. So what we do is there will be a dependent variable which we call it as a output y, and you will have an independent variable also which will decide your dependent variable based on this particular equation. Okay. So here there might be many data points over here which will actually do the classification between your what forms the other and the next one. So here basically in your simple linear regression you have to note that the variables, dependent variables would be got based on your independent variables. So one example I am taking over here for your case study. So if you want to predict CO2 emission, you are in Pinia industrial area, right? So carbon dioxide emission is more here. So all of you know about it. So if you want to do some projects based on that, you can use a linear regression model for it again. So here it is a CO2 emission with engine size feature using the simple linear regression. So your data set would look something like this. Whatever I have shown over here, it would look something like this. So depending on your engine size, you are able to track your CO2 emissions. So what you usually do in ML model is you train your machine with the available data. Okay, so these are called as what? Yeah, training data. Okay, then you have some unknown values. That is, you call it as a test data. You want to test a new value to it. Okay, so what you do is, for example, if I take over here, say some 1.5, the carbon emission is 136. So 1.5 around you check, 136 should be the value over here. So like that you will keep on plotting all the values of your x and y axis. So only two things we have taken, right? So only your engine size will be plotted across your x axis and your CO2 emissions would be taken at the y axis. So simply plot the graph. Okay. So when it comes to all this, your ML model would be able to track until here. So your model would have been trained, telling that if these are the values, this is the output carbon emission that has happened, carbon dioxide emission. Okay. So now you go for the test part. Then you check if the engine size is 2.4. So what should be your carbon dioxide emission value? So in that case, what it will do is this straight line it would have already got, because of the linear regression model that you are using, would have got that line already. So now at 2.4, this is my question, right? 2.4, what should be your carbon dioxide emission? So at 2.4, I will put a intercept at this. So I will get a value as 240. So now I am able to predict. Okay, so now the machine learning model, what you have trained, is able to predict if any new value is given as 2.4, the output would be 214. Got it? So this is the linear regression model. Hope it is clear. Next. So if you want to code for it as a CSE students or math and computing students, basically you want to code your linear regression model. It is very simple. Everything is inbuilt, libraries are there. You just simply need to import it. But why I told the mathematics behind it is, in order to make any model, mathematics is very much important. Statistics is very much important. So with that, we go with the coding part. So from sklearn, you try to import the linear model and put the variable as linear model dot linear regression, and you have to just divide your x and y. X is your input, y is your output, that is train and test. X will be your input, means you are training the model. Just now I told you. and similarly y is your output. So for that you can use any array and use a train of values for your engine size, because that is acting as your x-axis for your inputs. What was your output? Output is carbon dioxide emission. So that you give it as a y, train y. Okay. So like that you will put the values. Then you need to fit it into your model. So x train and y train, you fit it into your model. That means you start training the whole thing, putting the x values and the y values, and the different coefficients that you get and the intercepts that you get. I just now explained with respect to the graph I showed. Okay. So you will be able to predict any new value coming in, as this value will be the output. Okay. So next. Multiple linear regression, instead of having only two values, one input, one output, if your output is dependent on many different values, so under that case you go for the multiple linear regression. So you have a dependent variable, you have many coefficients and the inputs as x1, x2, which is explanatory. So you can use that, and any random errors are there, that would be termed as epsilon. So the same concept what I told you for single input and single output would be the extension with respect to multi-linear regression. Okay, so only one output will be there, but many inputs will be there, so along with the coefficients which are changing the values of your inputs. Okay, so this is how the multiple linear regression will work. So for multiple linear regression, if I want to take the same example of carbon dioxide emission, I had taken only engine size previously. So now I have made it as a multiple linear regression. So under that case, I need to take many different values. So let me take engine size and cylinder. So based on these two values, I will predict my CO2 emission. So this will be the change with respect to multiple linear regression. So now similarly, you can plot the graph for both the things. Try to get what will be the value for this one. Okay, so that's how it is. So when you do the coding, instead of just taking the engine size, now I take it as cylinder as well. Okay, so the same code will hold good, but instead of only one input, now I will be taking two or more inputs. So that is why it becomes the multilinear. So there is one more thing called as a polynomial regression. So in polynomial regression, what happens is you take the power of your x value. So instead of taking just a straight line, you can go with some curves as well if you take the polynomial regression. So that's why the equations would be looking something like this, wherein you have x square also being incorporated over here. Okay, so it is the power of 2 we have taken for this case. So what we were getting for linear regression is only this green color straight line. But if you apply it for a polynomial, since the square value is there, the values that will change with respect to x and y would look something like this red color. Okay, so that becomes your polynomial regression. So now for polynomial regression, the only change is instead of taking the engine size and cylinders together, we need to add one more value because it is multiply squaring the engine value. Okay, so twice we are taking the engine size value. So accordingly, your code will also be changing because you have to train your x models with respect to the square polynomial equations. So next is decision tree regression. So in decision tree regression, what we do is you will try to follow a tree structure. So basically you will have a root node, then you can have some intermediate nodes. Okay, so all these are the intermediate nodes, and then you have something else. This is called as a leaf node. So like this it can go on. Only one side I have written. The same kind of structure can follow for many others as well. Okay, so it follows a tree kind of a structure wherein you start with the root node and end up with your leaf node. Okay, so what you try to do is, if you given a very big problem, okay, similar to your modular coding, you cannot write everything in your main file, right? So what you try to do is write a function or write a sub-function, something like that. So similar to that, if a given big problem is there, what you do is you try to divide it into sub-problems. Okay, same way here, this is our main problem over here. Main problem statement is our starting from our root node. We try to divide it into sub-problems. Okay, so that's why it goes on. You can just read there. Decision tree builds regression models in the form of a tree structure. It breaks down the data set into smaller and smaller subsets, while at the same time an associated decision tree is incrementally developed, as I have shown on the board. Okay, so the final result is a tree with decision node and the leaf node. So finally you will end up with making a decision which one is better. Okay, so one example we will just take it for this to understand. So if you take a outlook, so for example you are taking the condition of a climate or a weather condition. So under that case it can be temperature, humidity, windy, those things can vary your temperature or your weather. So the outlook can be of three types, whether it can be sunny or it can be outcasted, overcast. That is, overcast means what? Like cloudy. It's very much cloudy, it is not raining, it is not sunny also. So under that case we call it as what? Overcast, and then you have the rainy. So three types of things are possible from the outlook. Can you see here? So the same things I have divided in the tree format over here. So the outlook can be divided as three parts, either sunny or overcast, or it can be rainy. So like this. So now if we want to do a hourly prediction, what can be the weather or the climate? So what we do is we apply our decision tree regression. So decision tree regression is usually for your continuous value, not for the discrete value, as I have explained earlier. So here also what we do is, depending on the temperature, humidity and the windy things, we take into account the target, that is our output. Output is hourly prediction, what we make for the weather or the climate. So you can end up with, it can be windy, true or false, how much percentage, what's the value based on which you can do the predictions. Okay, so this kind of data set, if it is given to you, what you try to do is you train your ML model with the given data set, you keep some part as your test data set, then you check what will be the prediction at this hour. Okay, so something like this. So now what happens, it depending on the tree structure, what you are able to tell, if it is windy, true is coming more or false is coming more. False is having more value. That means it is not windy. So that is a prediction that your model makes. So similarly for the other two reasons, that is overcast as well as rainy, it will check the values. Whichever is giving you the better result, based on that it will take the prediction. Okay, so the leaf node or the decision trees would be based on this kind of a concept. Is it clear to all? Random forest regression, it is actually a combination of many decision trees. Okay. So it will be something like this. Many decision trees are there. You are taking all the decision tree. Individually you will predict what will be the climate. Okay, windy, rainy, all that stuff. Then you take an average of all that. Sum is actually the average of all the random tree predictions. Okay, then we call it as a random forest prediction. So random forest is nothing but combination of many decision trees. That's all. Okay. So then you take an average and try to get the output. The same procedure is written over here for the approach. Okay, step by step procedure. So in order to come to the code, what you do is import the regressor, import the decision tree regressor, and you try to write what is the random state of it. Starting state 0 you will start with, and you assign it to the thing and fit your x and y train. I have not written the whole code as such. It's only a pseudo code for you to understand how exactly you should start doing it. Okay, so this is how it goes. And there are many pros and cons of each and every model. So since time is not there, I hope I will leave it this to you just to check how the different models are working. So next is logistic regression. So in today's class, I thought I will go in depth with the logistic regression. Okay. So in logistic regression, most of the statistical things are used, because what happens is we have something called convex and non-convex things and optimizations to be done, and we use gradient descent, so many things which you have not heard. You might be hearing it for the first time, as the first year students are also there, as I can see. Okay, so I will just start from the scratch and I will try to improvise it. Okay. So in logistic regression, it is a logistic regression model is basically totally dependent on your probabilistic model. Okay, so probability will be taken into account and it will be dividing certain classes or events existing such as pass or fail or many different. Other similar to this also, whether an image contains a cat, dog, lion. So many variables are there over there. So up till that you can go for your logistic regression. So based on the number of categories that you have, it can be having either binomial. Binomial means only two values, right? So either 0 or 1. Only two values will be there, similar to your binary classification what we saw. It is called as a binomial logistic regression or multimodal. Multimodal means it can have 3 or more possible types. So under that case, one example, either you can have a disease A, B or C. So like that. Okay. Or you can have ordinal also, in which you have a ordered category. Ordered category is in the sense like the student is good, very good, excellent. So many categories I am giving to a student. So all those are ordered, in order only, because I am talking about a single student might be having many different kinds of things. So those things are categorized as ordinal logistic regression. Okay. Now, so we start with the binary class problem. So what we see usually here is in linear regression we have lots of problems. So that's why we go with the logistic regression. So what are the problems that we face in linear regression is whenever we take say some we are looking into some cancer output or something. So input is your tumor size and output is malignant or benign. So whether the cancer cell is present or not, tumor is there or not, that you are going to check. Okay. So in this case, if you take the linear regression, then the threshold of the classifier output can be either very less or more. It cannot give a proper prediction because if the tumor size is something like this, as shown in this particular graph. So malignant or not, because 0.5 is there, I am not able to find out whether it is having a tumor or not. Okay, it is not giving a continuous value, only 0 or 1. So if it is in between like this, it will be a problem for you to decide. So that's why we go with the logistic regression. So in logistic regression, we use, it is a classification algorithm. You have to remember. Okay, logistic regression is a classification algorithm. And since we are using a sigmoid function to it, so there is something called as a sigmoid function to it. So we will add that sigmoid function. Usually linear regression would be represented like this. H theta of x is equal to theta power tx. So what is the meaning of this is, h is nothing but the hypothesis that we use in the statistics. Okay, that is to get the hypothetical output what we are expecting, and theta power tx, theta is actually the performance parameter, because here we are taking the size of the tumor. So that is acting as your performance evaluation parameter. So T is nothing but transpose of that matrix. If it is a column matrix, it will become row matrix. That's all. Okay, so transpose. So T stands for your transpose and X is your input. Okay, so this is for the linear regression. Because I have only X and Y, I will just plot a single graph. But when it comes to, this had a problem, right? Linear regression had a problem, just now I showed you. So now we go for the, what is that, logistic regression. So in logistic regression, the hypothesis is represented as G of T power transpose of X. So what is this G function? So G is very important over here, that is the sigmoid function we'll be trying to use across it. And the sigmoid function has this equation, this generic one. So there is a derivation and other stuff, but we are not going in depth of it now. So as of now, you please remember for the sigmoid function, G of Z is given by 1 plus e power minus z. Okay. So now, if we apply the sigmoid function to our linear function, then our hypothesis, that means whatever the output we are trying to predict out of logistic regression, will change accordingly. So it will become 1 plus e power minus t transpose of x. Okay. So this will be the equation that we use for the logistic regression instead of this in the linear regression. Okay. So you can see that logistic regression, sorry, linear regression was just like this. But when it comes to logistic regression, it can have a value which can vary apart from 0 to 1, any other value. It is not a straight line. Sigmoid function will be something like this, S-shaped. Correct. Okay. Yeah, this is the S-shaped curve I was talking to you about. Now you can see it is not varying between only 0 and 1. It is varying from minus values to plus values. So you have a larger scale through which you can fix up your problem of classification. Okay, so that's why rather than considering the linear regression, you can go with the logistic regression. Okay. So here you can see that at 0.5 it is crossing that line and flattens out only at the asymptotes, that is at 0 and 1. So asymptote means what? Continuous value which is not actually finally touching your values. So that is called as asymptotes. So that are available only at 0 and 1 values. So how do we interpret this hypothesis of logistic regression? You have to understand the mathematics behind the how actually logistic regression has come up and how the statistics have been useful in doing this. Okay, so when our hypothesis h theta of x outputs a number, we treat that value as estimated probability that y is equal to 1 on input x. Okay, so with this feature, we are just trying to tell that probability that the output is 1 when your input is x with the parameter value or the performance evaluation parameter. For example, that cancer thing I told you, tumor size. Tumor size will become your theta value. That is the feature that we are looking into. Okay. So now we have to have a mutually exclusive. That means all the events cannot happen at the same time. Okay. So that's why we write it in a mathematical format telling that p of y is equal to 1 at x theta plus y is equal to 0. Both cannot happen at the same time. So both should be equal to 1. So whatever we are talking in English language, the same thing we are trying to predict it in a mathematical format over here. Okay. So this is the mathematics behind your logistic regression model. So here you should see that there should be a decision boundary because we are actually using the ML model to do the predictions. So predictive analytics is the major thing in your ML model. So any model that you use, it should be able to predict something. So that is what is our requirement. So when it comes over something like this, we have to have a hypothesis telling that if it is beyond this threshold, I will take it as some output. If it is below this threshold, I will take it as some other output. Okay. So based on that thing, we will just look into the sigmoid function. If g of z is greater than or equal to 0.5, when see, I have put a threshold as 0.5 now. Okay. So if this value g of x is greater than this, then it should be falling with the upper value. If it is below this, then the lower value. So that's what we are trying to write it here. Theta to the power of transpose, theta transpose x should be greater than or equal to 0. Then h of theta should be greater than or equal to 0.5. So are you doing the predictions now based on the value? Okay. So since you have taken the threshold as 0.5, it should be there above or below. You solve that problem of linear regression over here. Okay. So like that you will take it into account. One example we will take up here. So I have just given one equation over there. H theta of x is equal to g of theta naught plus theta 1 x1 theta 2 x2. So this is the equation with having two variables x1 and x2. So I am plotting the same thing x1 and x2 in my graph over here. Okay. I have taken the circles and also the cross. Okay. So those two signs I have taken over here. So now if I consider my theta transpose row vector will be what? In column wise it was this. If you take the transpose it will become row. That's what I told you. So the value will become what? Minus 3, 1 comma 1. Clear? So this will be your theta transpose. So now what does this mean is actually if y is equal to 1, if this equation is greater than or equal to 0, that's what we are trying to check it. So what is your conclusion? Can we segregate it into two parts because we want this as a separate one, this as a separate one. Okay. So under that case, what we write is minus 3. These values I am using in my equation over there. So what do I write? Minus 3 plus x1 plus x2 because both are 1 1. I am keeping it 1 1 only. So this should be equal to greater than or equal to 0. So if I take this, then it becomes x1 plus x2 should be greater than or equal to 3. And now if x1 and x2 should be equal to 3, what does that mean in my graph? In my graph it means I am dividing the whole thing at third point. So that becomes my boundary to divide the two things, to do the classification as circles and crosses. Okay, so mathematically we will try to find where is that border line to divide your whole data into two classified parts. Okay, so now we got it as 3. So this 3 I will put a decision boundary. Okay, so it is telling you this is circles, this is x. So y value will be different. Y will be equal to 0, output will be equal to 0. That is your model prediction. Because you told y is your dependent variable which is dependent on your x value and theta, right? So here when I am getting this boundary, I am telling y is equal to 0 means what is my output prediction? What will be my output prediction? Is it circles or cross? Circles, correct? So if my y is equal to 1, my output is crosses. It becomes very simple for you to do the segregation and do the classification. Is it clear to you? So that's how it goes with the logistic regression. So now can you tell me with this? I have increased one number, x2 square I have added over here. Okay, so if I add x2 square and I am assuming, this is the assumption I have made, theta transpose is minus 1 0 0 1 1. So this is the assumption that I have made. Okay, so based on that, if I apply this, what I will get? If I substitute in that equation, minus 1 plus x1 square plus x2 square should be greater than or equal to 0. This is what I get when I substitute my theta transpose value in the upper equation. Okay, so what do I get? The condition to do the segregation or the classification is x1 square plus x2 square should be greater than or equal to 1. Okay, so now all these within the y is equal to 0 will be circles. Outside that value of y is equal to 0, it will become y is equal to 1. So now I have divided the decision boundary as what? 1. So up till that one value I will put a circle, all others I will put it as y is equal to 0 and other one as y is equal to 1. So that helps me in doing the classification about the inputs. But there is one problem over here, because in any model that we take there will be some errors. Okay, so we need to take care of that error. All of us know error should not be there, it should be minimum. But still when practically we do, there will be some errors that is being their part of it. So that's why we take one thing called as a cost function. Okay, so cost function that is used for logistic regression is represented by j of theta. So cost function is represented by j of theta. So it measures the error of a machine learning model predictions. Okay, error is represented by what? Y cap. Okay, and against the true labels. True labels are what? Actually without any errors, whatever we get that we are putting it as Y. Okay, so using this convention we try to minimize our cost function using our theta value. So that is the requirement. Okay, so now the cost function what we do in logistic regression, that uses actually something called as a mean squared error. So when you do the standard statistics, there is something called mean squared error. So all of you know about it. So this mean squared error is used actually in this non-convex function. So it will become a non-convex function when we incorporate our sigmoid function into this particular logistic regression. So that's why it becomes a non-convex function. I'll explain you what is this non-convex convex also, so that it becomes easy for you to understand in the next slide. So as of now, you please remember that this j of theta, it is actually dependent on your loss function, which is a log log equation, log function equation, and that is given by these two values, L of y cap and y over all the samples or the examples that you take. Okay. So m is the number of training examples, that is this value, and theta represents the model parameters, that is whatever the weights and biases which we want to add on, and yi is actually the true label as I have written over here, and that is for the ith example I have taken, so that's why I have written y power I. Next, y cap is actually the whatever the outputs that we get using the sigmoid function with error, so that is y cap of I, and that is the sigmoid function which I told you previously also. What is the equation for the sigmoid function? 1 by 1 plus e power minus z. So I have told you already, so you are aware with it, so that we are using. But this is the function mathematically our logistic regression will use along with the sigmoid function. It is called as a binary cross entropy loss or log loss. So this is the loss we use to do the calculation. Okay, so this loss should be more or less, it should be minimal. We should try to reduce it. So this log function is given by these two equations. So because if yi, our true values are 1, then it simplifies to minus log y cap of I. I am not going with derivations of all this, but you can remember this. yi is equal to 0, then the loss function will become minus log of 1 minus y cap of I. So these two combined together, we are getting this particular equation, which is the loss function. Taking y is equal to 0 and also y is equal to 1, we are able to give two values in our log format, that is called as what? Binary cross entropy loss or log loss function. Okay, so this is the log loss function that we need to use it. Okay, next. So with this, all the background, what we are most interested in is our cost function. This is our cost function, right? J of theta is our cost function. So here J of theta will become 1 by m sigmoid of 1 to m, all the samples, considering the sum of all the samples, your log loss function. Okay, whatever the equation I wrote now for the log loss function will be substituted over here. So it's log value and also 1 minus y value. Okay, so this will be the final cost function equation that you get. So I was telling you, whenever we add this sigmoid function, along with our logistic regression, I told you it will come up as a non-convex problem. Okay, so non-convex function. So this is the non-convex function I was talking to you about. When you plot your graph in any of the simulators like MATLAB or anything, you will get a non-convex function like this, and this is the convex function. Okay, so what happens is, whenever you use a non-convex function, what problem you can face is, we want the loss to be minimal. Okay, but what happens in non-convex function? You can find the minimum of this, you can find the minimum of this, correct? In non-convex function, you don't have a regularity, basically. Many dips are there in between. Ups are there, downs are there, like that you will get a graph. So it becomes very difficult for us, which will be the minimal value to calculate your loss function. Are you getting it? Are you getting it? I'll just write a simple graph over here instead of the 3D, so that it becomes easy for you to understand. Okay. So what I am talking to you about is this convex function. So what is happening with this convex function? I can have a local minima because I want the loss function to be minimal, right? I want the loss function to be minimal. So I can have this as one of my local minima if I consider only this part of my graph. But here I have one more local minima if I consider only this part of the graph. Are you getting it? Okay. So such kind of higher ups, lower ups, whatever you are getting, that will be part of your convex function, which is part of the logistic regression which you use along with the sigmoid function. Okay. So this kind of a graph you will get when you run your logistic regression. But this is not optimized, right? Because I'm not getting the overall loss function which is minimal. I'm getting a local minima here, I'm getting a local minima here, correct? But what I want a global minima, correct? Global minima is, I should take everything into account and I should find my lowest value for my loss function. So that is called as what? Global minima. So how do we achieve this global minima? So in order to achieve this global minima, we use something called as a gradient descent. Okay? So gradient descent we will use in order to have the local minima value so that we can convert our non-convex function into a convex function. So in this convex function, are you having only single minima? Okay? So that is done by using the gradient descent. So how do you do this gradient descent is, you imagine, okay, convex logistic regression, the equation is given by the cost function, given by this and this, together you got your g of theta, that is the cost function together. Next slide. Next slide. Here. So always this gradient descent, what I am talking about, it will always assume that it is on the top of the mountain trying to reach the lower end of your mountain, because I want the loss function to be less. So imagine yourself, you are on the top of the mountain now. Okay, you are following the gradient descent. Okay, how do I go down to my below value? So I have to take something called as a step size, which is called as delta. You cannot jump directly from the cliff to the bottom, right? So you take step by step to step to go to the bottom of your mountain. So the same concept is used in your gradient descent as well. Okay. So what they do is, it will start from the starting point of the mountain. It will take step by step. So that is called a step size. In each step size, it will start moving below the thing. Okay. And after it reaches this, again it will start moving down. But then it will find out that this is the optimum value. So it should not go down still. Are you getting it? So that's why this point, which is the optimum value, will be got using your gradient descent in the step size and other stuff. Okay. So this is what is the thing shown. You are on the top, you move it step by step until you reach the bottom point. Why you are reaching that bottom point is because you want your loss function to be minimal. Okay, gradient descent is clear to you. So what this gradient descent will help you is, it will try to convert your non-convex function into a convex function, use the step size to reach your global minima in order to reduce your loss function. Okay. So similarly, you can have a multi-class classification problem as well. Instead of having only two values, you can have many different values like this. Then we call it as a multi-class. Each one is taken as a class. Square or rectangle, that is taken as one class. Triangle is taken as one class. Cross is taken as one more class. So you have to have many different classes. So then we call it as what? Multi-class classification problem. So here, what we try to do is, instead of directly jumping the things, what we can do is, we can just convert our thing into a binary classification first, using the logistic regression, do a binary classification, then use those predictions to get the final multi-class prediction. Okay, so that is what is shown over here. So I have taken the triangle versus crosses and squares together. So this I am taking it as one class. Crosses and squares I am taking it as one class. I am taking triangle as one class. I am trying to make the predictions similar to how my binary logistic regression I just showed you now. Okay, how it will divide into two parts. So it is giving me something like this. Some results it is going to give me. Okay. Similarly, I am taking the next class as crosses versus triangles and squares. So all the combinations I will make. Okay. And I will try to keep only two classes at a time. Do the prediction which one is better. So once I hit the predictions of all, the core idea is to break the single k class classification problem into k separate binary classification problems as I did just now. Okay, 3 classes we had. 1 class I will take, 2 I will combine. Okay, so I made it as a binary classification problem. So after that, making the final prediction, what we do is we will take the argmax of the overall predictions that we have got from all the 3. Okay, maximum predictions whichever is there, that we will conclude it to be the final one for our multi-class classification. Is that clear? So next is k nearest neighbors. This is one more algorithm that we have. So in k nearest neighbor, what we do is we will just try to find, right, who is alike. We will become friends with them only. Correct? So what we do is whichever is having the similar characters, we find it is good, we'll try to mingle with them. The same way here, k nearest neighbors, what they do is they will try to find based on your distance, based on the distance, which is the near one, which is the farthest one, and which are the similar classes, which I can make it as a group. Okay, so these two things are there. So here choosing the distance is one thing, taking the distance into account is one thing, and apart from that, taking the similar cases is the second thing. So 2 things we have to take care in the k nearest neighbor. And the distance calculations can be done using the Euclidean distance equation, regular Euclidean distance equation. This is one method. There are many other distance methods that you can use. We'll just see with one example. Say for example, you have x independent variables and you have y dependent variable. So y dependent variable is what? Customer category. So customer category is your output y. So many independent variables are there, region, age, whether married or not, address, income, so many things are there as your independent variables. So what we try to do is we will try to label and give a value for your y or dependent variable. So I have given the values as 1, 2, 3, 4 and the labels as basic service, e-service, plus service and total service depending on the particular customer values. Okay. This example I am going to explain with respect to k nearest neighbors. Okay. Next. So now you will get many data points whenever you are plotting it on a graph. Okay. So different colors are used for representing different kinds of previous. Here only this. Next. On the top you can see blue color is for the basic service. And e-service is some other color, yellow for some other color and some pink color. Okay, so 4 different categories we have considered. We have given 4 different colors for it to understand which is similarity. Because I told you similarity is important and also the distance is important. Okay, so similarity, what we are trying to do is we will try to find which is the same color. That is the similarity. What is the distance? Distance is actually the k value. There is some value variable that we choose as k in k nearest neighbor and we have to choose this k value very intelligently. It cannot be very low, it cannot be very high. It has to be optimal to get a very good result. So that is the requirement. So under that case you can see that if I consider k value as 1, k value as 1 if I take, which is the very nearest one, this blue color is the nearest one to this particular data point. Okay, so if I take this, I am not getting any other similar patterns. The blue color ones is not there over there. So it is not giving you a actual good output. The model cannot be having a good accuracy. Okay, so what it tries to do is, it will change the value of this k. Okay, if I take the k value as 4, I am getting 3 nearest neighbors to it. If I do the calculation using any of the distance parameter, Euclidean distance or whichever, you will find that these 3 are nearest to you and there are the neighbors to each other. So that is the best option compared to the blue one. Correct or not? So based on this thinking, k nearest neighbor will give you the best value. Next. So which was our proper thing? K is equal to 4, that is the pink colored one, that was giving the better result. So k nearest neighbor, it will use 2 things. One is k value and one more is the distance and similarity. Okay, so based on this, it will try to find the similar kind of a value and it will be able to predict which value is giving you better accuracy for the model. So this is the concept behind your k-nearest neighbors. So there are few advantages and disadvantages because it is dynamic. So as and when the data comes, it will find. There is no training period involved, and also predictions, whatever we are making, it will have a lot of impact on the accuracy, as now just I showed you with the example, and it is very easy to implement also. These are the advantages. Coming to disadvantages, it does not work well with large data sets and does not work well with high dimension data also, because only 2-dimension XY if I take, it's easy. If I increase the dimension, it will have a problem. Sensitivity to noisy data, missing values and outliers, that is also one more problem. Outlier is outside the, for example, just now we saw that blue and the pink color. Outside that particular value, we call it as an outlier, which is not part of the particular thing. We are not near also, it is far. Then we call it as an outlier in k-nearest. So this is the implementation. As I told you, import that k-nearest classifier and try to get your prediction based on the probability. Just now I showed you that pink color probability is more, which will give you better accuracy. So the same thing will be holding good if you code it. The last one is support vector machine. The time is out, so this will be your last thing for today. Support vector machine. So as you can see, support vector machine is actually classifying your overall data with respect to the dimension. Next, please. Next. So it will be something like this. So I have in 3D dimension, just imagine it is a hyperplane that is being created using the support vector machine. You will have a lower data which is yellow color, and you have a blue color area above the hyperplane. So what your support vector machine is doing is dividing or classifying things using the hyperplane into account. So it will actually show this kind of a thing. This hyperplane is actually segregating your blue colored ones with your yellow colored ones data points. Okay. So it will become easy for you to do the classification. This is a method used in the support vector machine. So in the same way, you can see over here also that red color is the hyperplane. This is in 3D, that is in 2D. Okay. So the red colored one plane, whatever you are seeing, the data points with red colored and the blue colored, you have a margin given to it, and with respect to that, you segregate using the hyperplane. Okay. So this is the support vector machine. So this is actually the hyperplane, what I was showing you. Okay, it can be of any size, it cannot be always the straight line. It can be in this way also. In 3D, if you imagine, it will be easy for the support vector machine. So please remember, hyperplanes will be there to segregate your data points, which can do the classification. So that is a method used in the support vector machine. One example given over here is again the tumor, either benign or malignant. So two types of cancers we are trying to detect using this data points. Okay. So I am just trying to help you out with the mathematics used in the support vector machine. If you just take a single dimension data like this, it will be represented as phi of x is equal to x comma x square. The same thing if you take it with respect to x square, you can divide the whole plane as x and x square. Two values you will get. X as one of the plane and x square is one of the plane, but the hyperplane of your SVM will actually do the classification of both the regions. Okay, probably I am not going in depth with SVM. There are a few advantages and disadvantages with respect to your support vector machine. Advantages is accurate in high dimension space because you are taking the 3D into account. So high dimension space when you are going with SVM is good and memory efficient also. And disadvantages, small data sets will be difficult and is also prone to overfitting your model. Okay. So some applications of your support vector machine are image recognition and spam detection. So image recognition you will learn in detail in the computer vision subject. Okay. And spam detection is also one of the applications of SVM. There are many other algorithms also like naive-Bayes algorithm and naive-Bayes classifiers. Okay, we have clustering also in unsupervised, as I told. Naive-Bayes will use the Bayes theorem only. Okay, So it will try to do the probability prediction, taking the prior values, what will be the posterior probability values. But I'm not discussing because of the time shortage. But please remember. Next, sir. Thank you. Good touch. So this is the equation using your Bayes theorem. Okay. So you are trying to predict your posterior values using your priori values. So that is what is the Bayes theorem is all about. We are not going in depth. Some other time, if you find time, we'll definitely discuss about it. Hope it was helpful to you. Any questions? Thank you. Thank you so much. Any questions? Hope it was helpful.
Any questions, audience? So I thank Dr. Jyoti AP to enlighten us about different machine learning models and giving more emphasis on the important machine learning models such as linear regression, logistic regression, decision tree, SVM, etc. Thank you, ma'am. So our next session is on fundamental logic behind big data analytics by Dr. Subramaniam T, Assistant Professor, Department of Mathematics and Statistics. Dr. Subramania T is a highly distinguished member of the Faculty of Mathematics and Physical Science, RUAS. He brings in 17 plus years of academic experience as a guest faculty, assistant professor, associate professor at various esteemed institutes such as Sri Venkateshwara University, Pondicherry University, and Christ University. He is vastly experienced in administration as director for the research center, department head, etc. He visited universities in Hong Kong as a part of leadership exposure visit. So he has a total 30 plus journal publication in Scopus, Web of Science, etc. and 20 plus conference papers. He has conducted and attended workshops, symposia, quality improvement programs and faculty development programs, etc. So I'll hand over to Sir. Thank you.
Thank you, ma'am. Good afternoon, all of you. Actually, my title, Statistics, the foundational logic behind the big data analytics. This is just like the statistics foundation for analyzing the data actually. But maybe as a computer science students, you are calling as a big data because your systems are capturing the data and you are only making big data and you are only trying to analyze the big data. But generally what happens? So the data, whatever is required, we are collecting the data and that data we are analyzing. But generally what happens now, automatically we are collecting the information. Is the information is required or not, whatever may be that, we are collecting the information and we are storing the data. And finally, we are getting the difficulty to get the meaningful insights from the data again. So that data only we are calling now it is a big data. So now we need to solve the big data because we only created the big data. Now again we are only trying to solve from the big data. So this is the one side it is a good, one side it is a difficult situation for us. Okay. So now actually when I start thinking about this one, because the title of this workshop itself, Statistics in Data Science and Machine Learning. So we have planned so many advanced level topics, everything. Then I thought maybe I can give a very basic idea about the statistics. So for the participants, really how the logic works for analyzing the data. So generally what happens in statistics, there is a fundamental assumption is there. If the data is less than 30, theoretically, then we can consider it is a small data. And if it is a greater than 30, less than 30, it is a small sample data. It is a greater than 30, we'll consider it is a large sample data. Whenever you are considering greater than 30, even if you take 1 lakh observations also, the statistical assumption is same only. So you consider if it is less than 30, other assumptions are different. If you consider greater than 30 observations, the assumption is same for even 1 lakh observations, or maybe if you take 10 lakh observations also, the assumption is same only. But only the question is here, how the characteristic will change. That is only the thing we need to observe in that place. So for that reason, I thought, okay, let us will give some basic idea about the statistics, how we are using in that place. Maybe I think maybe that our students are there, you are also studying now property statistics. So some of the things will repeat here. Okay, so this is the first question. Actually, in inauguration also I said this point. So in the era of big data, whatever the data we are generating the data, what is the true power of the analytics? This is the question actually. The power of the analytics is maybe it is the storage of the capacity or computational speed. So what is that? Maybe storage capacity, because we are able to now collect the data and store the data. Maybe first you said maybe what is gigabyte. Maybe first you said megabytes, then you call gigabyte, then you call terabyte. Like that, every day you are expanding, expanding, expanding. You are trying to store the data. Okay, that is the analytics. Otherwise, next one is computational speed. First, we have started analyzing the data with a small data. Maybe some 100 observations are there. Maybe then after that, 1 lakh observations. Maybe it's audible? Audible? Okay. So maybe I have to use this.
You have to use this because online participants.
Okay. Oh, I think it is audible now. Oh. So the first one is storage capacity. So already we are reaching to the next level. Every day we are trying to expand our objective to increase the storage capacity. Next one is computational speed. So now day by day we are trying to work on that one, how to increase the speed of analyzing the data. Maybe we need more speed is required. So like that, maybe to if you see today, maybe you are calling as a different maybe the system, how much speed. So the RAM you are increasing, other one, because we need more speed is required to work with the large data sets. So these two things, whatever is their storage capacity and computational speed, if you are depending only on the two only, just we can collect the data and we can store somewhere, and we can maybe the computational speed means whatever the algorithms are there, that algorithms will become more fast, maybe fastly you can activate that one and we can do that one. Then the data maybe you can store in a place. Then other than that, what we can do? Because we need some meaningful information are there required. So getting meaningful information insights. So from that data. So whatever the data is available with us, so we have to get some meaningful insights from that place. So how we can get that meaningful insights? So directly, just like that, you can't take the data and you can't maybe analyze that one and you can't get the data now. So this is the big problem. So for that reason, so this third one is there now, getting meaningful insights. How we can get that one? Maybe mathematics is there, and maybe some other subject is there, some other subject is there. Which one helps in that place to getting the meaningful insights? So this is very important for us. The question is here, whatever the data you have collected, it is very difficult to utilize entire data set to analyze the get the meaningful insights. Anytime we are not going to use the entire data set. This is not possible. Because maybe you have some data, maybe less data is there, but still what happens, some missing data you can get. So we are not using 100% of the data whenever you are analyzing. And the problem is here, even if you collect the data, maybe some 10 years data you have utilized, and if you use the 10 years data also, you may get some meaningful information in a place, but the required things, whatever is there, that is not possible. The reason is here, once the time passes, your data also will lose the identity, will lose the importance. Maybe 10 years once, whatever may be the salary structure of some maybe the employees in industry, today what is the salary structure of the employees in industry, if you want to compare these two, and if you want to based on the 10 years one, today if you want to do that, so your total analytics will go wrong. So that is the reason the time passes, your some data is almost all it is going to become invalid. So it is not useful for us. Only just what we can do, some meaningful information we can get. So some trends we can see. After that, we have to depend the data, present data only we are going to depend. So that is the reason past data is there, present data is there, and what is going to happen for future. So that time your present data will help more and more to predict for the future. So now whatever we are talking about is modeling, predictions, everything is there. So predictions will come. So predictive analytics will come to in the next stage. So first we need to understand whatever the data is there. So this is very important. So now the third one. So I need to get meaningful insights from the data. How I can get the meaningful insights? So now the statistics forms the critical foundation of big data analytics, providing the essential tools for transforming raw data into meaningful insights. So now the critical foundation where we can get now from the statistics we can get. Maybe the statistics is from the mathematics only we got applied mathematics. So generally what we will call now. So statistics is the applied mathematics applied to the observed data. So in mathematics generally we are not applying for the observed data, but here we are in statistics the observed data whatever is there we are using that observed data and we are applying the applied mathematics in that place. Okay. So now how this statistics will forms the critical basis. So this statistics will explain you how to collect the data. So first one. Next one is how to organize the data. It will explain. So next one is how to interpret the vast data sets. That will explain. Okay. And you can complex data sets, everything. And how I can get the inferences from that place. That it can explain. So each one step, because actually maybe previous morning session, so in predictive analytics. So Yadavendra Babu sir said it is my favorite definition is this one like that. So why not? That is the reality we are doing in industry. So whatever in real time, whatever we are applying, that is the definition of statistics. So we are collecting the data and you are trying to organize the data and you are trying to analyze the data and you are trying to interpret the complex data sets and you need to get finally some meaningful information also from them. And now the analytical results, whatever you got, they are valid, reliable and meaningful in guiding data-driven decisions. So whatever the data you have utilized, whatever the results you got, that must be reliable and also valid. Anyone can cross-check that one and they need to get the meaningful information from that. So we can't hide that one because we are using the data, you are analyzing that, it is required to validate the results. So this is very important for us. Okay. So now you come to this one. Just maybe some idea I have given here. Maybe not only for you. So many people are there in our workshop also, other people. So once you have the data, so what is the next level? So the next level is you need to try to understand the characteristics. What are the characteristics available in our data set? That is very important. So whenever you have some data is there, maybe you have stored some data in that place, then you are not going to collect each and every observation in that place. You are trying to understand what are the characteristics present in that place. So for each characteristic, you are trying to extract the data in that place. Maybe, for example, the data is relating to the employees. So maybe their employees' experience. That is a one characteristic. You will extract that information. There maybe their gender. You can extract that information. So these are the characteristics. So first you need to understand what are the characteristics available in our data set. So these characteristics in statistics we call as the variables. So these variables plays a major role. Statistics deals with the variables only. So this is the first point. So we are not going to deal with a constant. So in mathematics we will call constant. So you say a equals to 10. Your entire whatever the calculations you do, it is a constant only. But when it comes to the statistic, we are dealing with the variables only. So that is the reason whenever you are dealing with the variable, whatever the characteristic you are taking, that will change time to time or maybe person to person, some other maybe time point to time point. So one region to other region. So it can change from one point to other point. So that is the reason we are calling it is a variable. So now once the variable, if you have identified, then you need to understand what type of variable is that one. So this is very important. Maybe can I can quantify that variable, or I can maybe it is not possible to quantify. So in terms of numbers especially. So quantitative variables means the variable can be measured numerically. So that variables we can call as a quantitative variables. So now you can see age, height, weight, or price of a commodity, like that, maybe all we can quantify. But when it comes to the qualitative variables, it can't be measured numerically, but based on the quality we can measure. So there are two things are there here. One is gender. If you take gender, what happens? Only you can quantify, you can do maybe what is the quantification here. So based on the maybe male or female, maybe others, like that, maybe you can say based on the quality you are saying. But maybe in a real time, if you go to some medical sciences, so they are also have such type of problems. So when you maybe some person has some stomach pain, like that, no? If they go and if they visit the doctor, that time they may ask how much pain you are facing. So too much pain. So like that, if they say no, then how they can measure that one? So here it is a quality only. He is telling that I have so much pain is there. But how the doctor will quantify that? That is the question mark. So for that reason, there are different scales. They will use different scales. So Likert scale, some other different scales in different domain they will use. So what they do now? They will convert that into 0 to 5 and 0 to 10, like that. So that quality, whatever you are saying, I have moderate pain is there. So 0 to 10 means moderate means on an average, maybe medium means until 5. So 5 number it will write in that place. He will write. And if you say too much pain is there, so he will say continuously you are getting, yes, I am unable to tolerate. Then too much pain means you are getting 8, 9, like that. He will put the number. So like that they will quantify your qualitative variable also into a number. So then they will analyze that, because statistics deals with only numbers only. So the qualitative data also you can convert into quantitative variables. So then you can use for analysis purpose. So that is the reason here we can use this every time we are dealing with quantitative variables only. But when it comes to the real-time applications, some qualitative variables are there, but that variables we have to convert into quantitative for further analysis. Because if it is a qualitative variable in statistics, very less analysis is there for that one. So we can't do any statistics, because statistics every time it explains only in terms of numbers only. So that is the reason here we need only in terms of numbers only it is required. Okay. So once you convert this quantitative variable and qualitative variable, so you have segregated that one. Then again further you need to understand what type of variable is there, that quantitative variable. Because here, if the quantitative variable, whatever you observe, it is assuming specific values for specific person. Maybe now students are there, each student has some marks. First student 20 marks, second student 25, third student is 30 marks. It is a discrete variable. We call it as a discrete. Specific values is assigned in that place. When it comes to continuous variable, by nature, the variables are in continuous case. So now temperature is there, continuously they will change. Your heartbeat is there, continuously it will change. Wind speed is there, continuity is there. So such type of variables will consider as a continuous variables. So you need to understand what type of variable I am going to deal. And I will tell you one thing, in statistics, we are not going to do any predictions for the continuous variables. We are doing only for the discrete variables. We are trying to convert the continuous variable also into a discrete variable, and we are making the modeling predictions. Because continuous variable that doesn't have any proper interval for that one. Means sometimes maybe nanoseconds it will collect the data. After that maybe half an hour distance gap is there. After that maybe only 1 second gap is there. So that time if you take such type of data, if you build a model for next level, what type of prediction you are doing? You are going for the 1 minute you are doing, or maybe 1 hour you are doing the prediction, or maybe half an hour, that we don't know. That is the reason generally what we do, we'll convert that continuous variable also into a discrete variable, we'll give equally spaced intervals, then only we can convert, we can model that variables, the discrete variables. Now, whenever it comes to qualitative variables, further maybe here we are going to divide into nominal, ordinal. The qualitative variables, other name is categorical variables actually. So they have different categories. Gender is there, male, female, others like that. Na? So different categories. Nominal variables means the categories doesn't have any order. You can write first male, second maybe female, or maybe others, or maybe you write first others, maybe next male, female. So there is no specific order. But when it comes to the ordinal variable, na, there is some specific order is there. So maybe in medical sciences, the doctor will explain what is the situation of that particular disease like that. What they will do, mild, moderate, severe. Mild means starting stage, moderate means next. Severe means it is the end stage like that. So there is a specific order is there. And maybe if you see the economic status, maybe low, medium, high, like that, some specific order. If you come to the education qualifications, so 10th, UG, PG, like that, if you want, like some specific order is there. And if you want to convert into your ranks, first rank, second, third, you can't write third rank first, then first rank, second rank. So that is not good. So there is no meaning. So for that reason, whenever you are dealing with this type of variable, first you need to understand what type of variable I am dealing. This is very important. So this is very important for us. So now you come to this place. This is very important for us. Okay. So now generally what happens? So whatever we are dealing the data, so it is a sample data one. Even it is a 1 lakh observations, it is a sample data. So we are not dealing with the entire data set. It is impossible to deal because maybe I am defining my own population. I need to give some meaningful information about the employees, those who are working in Bangalore like that. Then what happens here? Collecting the data is not possible in that place. So some sample data and maybe the system whatever it is generating in that place, you can collect the population means entire data is available. But finally, whatever the data you want, that data only you are collecting and you are trying to analyze that one. That is the reason it is a sample data. So you are dealing with sample data only, not with the entire data set. This is very important for us. Okay, so now this is my population. I have defined my population because population is an infinite population or maybe finite population. Population will represent different characteristics in that place and everything maybe it is available in that place. So from that place you can collect some sample data to represent your entire population. This is very important for us. So statistics has a very good methods here to collect the sample data itself. Just like that, I can't collect. Maybe, for example, if you want to say simply, maybe in a class, some 60 students are there. I need to select some 10 students. Just like that, I can't collect the students because maybe the randomness is required because the bias. I need to reduce the bias. So for that reason, so there are different methods are there to collect this sample data. Okay, so now if you understand this population, it is a huge population. From this population, I need to collect the sample data. So why it is required means every time I am dealing with the sample data only. So I am not dealing with population. So that is the reason. So I need to depend with the sample data. So let us you consider this sample data. Once you consider the sample data, what is the next step? I need to understand the characteristics of the sample data first. If I know the characteristics of the sample data, whatever the characteristics are there here, maybe these characteristics came from the population only. So the characteristics, whatever is there for sample data, it came from the population data only. Na? Maybe the population also has this type of characteristics. So this is the question mark. So really maybe that data, whatever I have selected, it is from this population. So whatever the characteristics are there for the population, if I analyze this sample data, maybe these characteristics are maybe representing your population. That we have to understand, that we need to see. So now the entire analytics is analyzing the sample data here. So first we need to understand the sample data, then you need to generalize for the next level. Okay. So now your sample data is available here. So now once it is available, so generally what happens here, how you have selected the sample data, they will ask. So in that place what happens in statistics, the question is how select the best sample. How you can select the best sample. This is the question mark. So in that place what happens, to select this best sample, so we have sampling techniques are there, sampling theory. So in that place what happens now in sampling theory, you have two methods are there, two categories are there. One is non-probability sampling methods, another one is probability sampling methods. So you can use probability sampling methods or maybe non-probability sampling methods. So in non-probability sampling methods, these are the convenience methods. So based on the convenience, okay, I can take only in the Spenia area only, I can collect the data and I can analyze, I can submit that one. But maybe if you want to go for what is that probability sampling methods, the entire population need to cover in that place. So maybe you said entire Bangalore, you have to cover the entire Bangalore to collect the sample. Maybe in that place what happens, you can get the sample data which can represent the entire population. So here, the logic is here, the fundamental logic is here, collect the sample with representing the entire population. So you select the sample in such a way that your sample need to represent the entire population. This is very important. So when you are collecting the sample data which is not representing your entire population, whatever the analysis you did, whatever you predict, that may not represent your entire population characteristics. So you may lose in that place. So that is the reason the sampling theory is there, that will explain how to collect the sample which can represent the entire population. So maybe for example, if you see in a class, maybe some 20 maybe male, female students are there, 60 maybe male students are there. Then if I want to collect the sample, some 20 students, just like that from females 10, males 10, like that I can't collect that one because a proportionate sample is required in that place. So that is the reason in sampling theory we have simple random sampling theory, stratified random sampling theory, systematic sampling, cluster sampling. So like this, maybe different. So based on the proportionately you have to select. But the government generally what they do now to represent the data, so they will divide first one state they will divide into different maybe mandals. So in the districts, on in that different mandals. So in that villages. So in this village, how many people are there here? So proportionately, how many I need to collect here? Proportionately, how many I need to collect here? So like that, if they collect, then only they can represent entire state information. Because you are not collecting each and every from the each and every person, you are not collecting. So the sample, whatever you are collecting, that sample need to represent how maybe that sample, whatever you are collecting, it needs to represent the entire population. This is very important. Okay, so next. Okay, so now just maybe I will come to this because whatever we are doing here, this is everything is depending, the connection is with the data science only, and maybe next level is machine learning. So generally what happens now, this machine learning concept, whatever is there, first we called as a data science, then we went to the next level. So in a simple method, I will tell you what is data science and what is machine learning. Your data science is your master's, machine learning is your PhD. So in a data science, generally what you do now, all the courses you will study in master's course. But when it comes to the machine learning, you will study only specific problem you will take and you will analyze that one. You will train the system to understand that one, and finally you will make the algorithms to work for that one, and finally you will go to the automation for that one. So that is the reason you are understanding here very specific topic only. We are trying to work in this place in machine learning because we are giving the training for the systems only on the specific. Just like that, you are not giving for the entire data you analyze and you give like that. We are not doing anything here. So when it comes to this data science, so what is the definition of data science? Broad and interdisciplinary field focused on extracting knowledge and insights from the data to solve problems and information decision making. So it is an interdisciplinary broad area. So you can use whatever the statistical methods to get meaningful insights. So it is a broad area. But when it comes to the machine learning, it is a subset of the data science that specifically focuses on building algorithms and models that enables computers to learn from the data and make predictions or decisions without being explicitly programmed. So here you are specifically trying to work only for one characteristic only in that place, and you are training the system with the algorithms, and you are making that to predict and other things, or maybe next level you need to do automation, other things. You are doing only specific one only. But here it is a interdisciplinary domain. So it is a vast area in that place. Okay. So next one is what is the scope? Focus on the entire data life cycle. So you can use in that place. But in this place, specific technical field is there, and a subset of data science and artificial intelligence we can use in that place. Okay. So what is the main goal in our data science? To extract actionable insights and knowledge to drive business and specific decisions. Okay. So what is in machine learning? To build predictive models that can learn from the data to make forecast or automation decisions. This is the ultimate goal in that case. So your machine learning will learn from the data only. So this is very important for us. So what are the specific tasks you are doing in data science? Data gathering, cleaning, visualization, analysis, storytelling. Storytelling means generally what happens now, whatever you do now, you need to create into one story and you need to explain that. So that is the storytelling generally. So next one is reporting. So these things you are doing. So in machine learning, what you are doing? Model selection, training evaluation, hyperparameter tuning, and deploying the learning algorithm. All these things you will do. This is a specific task you are doing in that place. So this one is the very important one for us. So now you have the data, and in the data science, what you said, I need meaningful information is required in that place. How you can get the meaningful information? There are generally what happens, you can summarize the data using the frequency tables and graphs like that. That is the one level. Next level is the three properties we have to understand. One is central tendency, other one is variation, other one is the skewness. We call these three because your entire statistics is depending on only these three only. Whenever you are going for modeling predictions also, only these three only will come in that place. Yes. Okay. So here what happens? The most number of observations will cluster somewhere in the distribution. That we call as the middle of the distribution. Somewhere it is there. So that we need to identify. We are calling it is the central tendency. So fundamental assumption is whenever you are plotting the data, majority of the observations will show tendency in the middle of the distribution. That is the reason we are calling it as a central tendency. So in that place, wherever the tendency is more, so in that case, we have to identify there is a one numerical value is there, surrounding to that more number of observations are clustered. So that observation, that numerical value, we have to identify. Next one is from that central value to your original observations, how much deviation is there. This we need to observe. This we call as the variation. Then third one is there. This is very important for us. The fundamental assumption is here, the data will follow the symmetric distributions. Generally we call it as a symmetric distribution. We call it as a bell-shaped curves. We call symmetric distribution. So the symmetric distribution generally what happens? It will divide 50% left side, 50% right side. The importance is given equally for both sides. So whenever you are going with this one, maybe it is a asymptotic. Maybe previous class it never touched here. So it is a asymptotic distribution. So this is the symmetric distribution. So you know about that. Central tendency means more observations are there. How to find out the central value? So using the mean, median mode, what is the averages will are more useful to represent that one. And to know this whatever maybe the central value is there, maybe here you will get. So exactly 50% here, exactly 50% here. So equal chance is given for all the observations in that place. Then only your numerical measures will represent effectively your data set. Otherwise, maybe if you go to this one, so whenever it is not there, if the symmetry is not there, then we call it as a skewed distributions. So next, yeah, you can find like this. So it is a symmetric distribution for me. So now here all the mean, median, mode will represent here. So 50% here, 50%, even the observation, whatever is there here, even the observation, and generally what happens here, the distance, whatever is there, that is very important for us. So now if you see here, it is a skewed distribution, and this is a skewed distribution. So whenever you are dealing with this type of distributions, your representation using the statistics may mislead. So this is very important for us. So that is the reason, if you see here, generally what happens, this type of distribution if you see, so yeah, like this maybe, you can see, maybe I have downloaded from this, learn statistics easily. So now this is the distribution. Majority of the observations will fall in this place. So generally what happens, 68% of the observations will fall in this place only. So now 68% of the observations are in the middle of the distribution, and the remaining only some 32% of the observations are there outside that. So whenever you are calculating your central value, that central value is coming here, and majority of the observations are near to that, and the deviation from your central value to this observation is very less, so automatically your standard deviation is also very less. The variability is very less in that place. So whenever the variability is very less, so automatically your statistics, whatever the number you are calculating, that number will represent effectively your data set. It is a big data or small data, whatever may be that will represent effectively. So now the logic is here, the fundamental rule is here, the distribution whatever you are following, the variable whatever you are talking, that variable need to follow symmetric distribution. This is the fundamental rule. If it follows that one, then whatever the statistics you are calculating, that will represent effectively. So this is very important for us. So now, yeah, maybe if you see here, this is a mean value, na? So the middle value, then maybe because of here standard deviations is there, maybe, yeah, because maybe the students already they know about this. We have discussed all, so that is the reason they are already saw this one. Okay, so now here see this standard deviation, the deviation is there, no? So this deviation. So from mean, this is plus 1 time standard deviation minus 1 time standard deviation. This we call as the 1 sigma limit. 1 sigma, 1 time. So this we call as, in industry they will call 1 sigma belt. Okay, then if you take two standard deviation limits, mu minus 2 sigma, mu plus 2 sigma, how many number of observations will fall in a place? Around 95% of the observations will lie in the interval only. So you are trying to represent by using your standard deviation here, how much the interval you are trying to construct. So whenever the standard deviation is less, so what happens? If you see here, it is a symmetric distribution. But whenever the variation, the standard deviation decreases, what happens? The standard deviation, the variation decreases, what happens? It will stress. So that time what happens? Your distribution will become like this. But such type of distribution is also not good every time. This is also very important. So actually here your distribution is, symmetric distribution is this, your symmetric distribution. But whenever your standard deviation, if it decreases, if it decreases, this distribution will become like this, narrow. So it will stretch like this. So that time what happens? This distribution is a symmetric only, but this case is there, this is again it is a problem for us because it is not a symmetric actually, because there is a too much spike in the mix, peak is there in the distribution. That we call as a kurtosis in the statistics. So you need to understand that kurtosis also. That is also very important. Just like that, maybe this is a distribution, maybe too much peak is there also. You can use that one. But maybe sometimes what happens, your data, whenever your standard deviation increases, what happens? Your standard deviation increases, this distribution will become flat. It will stretch like this. So your distribution may be like this, it may come like this. But it is not a, actually looks like it is a symmetric only, but it is a too much flatness is there. And it is this much is too much peakness is there. And actually the original distribution is this. So we need to deal, we need only this distribution is required for us. This type of too much flatness and too much peakness is not also good for our analysis purpose. So that is the reason whenever we are dealing this one symmetric distribution. So the first assumption is where more number of observations is concentrated. This is very important for us. And next one is how much deviation is there. That is also very important. Third one is the data is following the symmetric distribution or not. And what type of distribution? It is a flat or maybe peak distribution. So in statistics we call leptokurtic, platykurtic, platy means down, mesokurtic. So like that, these are the names. Okay, so now every time we are talking about this one, whatever is there, statistic, the variable, whatever is there, only one variable I talk about. So now you come to this one, regression, maybe because in the prediction analysis, what we are doing here. So mean is average value, standard deviation is the variation. So now if you come to this place, these are my original observations. These are all my original observations. It means for x value and y value, this is the corresponding number you have plotted. Maybe here x is maybe 2, y is also 2, means this is the point. Second one, third one, like that you have plotted original values, then x, y, whatever the values are there, we have plotted. So now you have fitted a regression equation in that place. Then what type of equation this will represent? This is a question mark actually. So it is a best equation like that we are talking in that place. Okay, so now if you see in this place, maybe it is a straight line, no? Just I will take it as a straight line. So if you take straight line, in statistics what happens? The randomness is also required. So I will consider as y equals to, so simple equation model I will take. So this is a simple regression model. So in mathematics we will call it as a y equals to a plus bx. This, but in mathematics randomness is not there. So here we are adding randomness. So this is a probabilistic model actually, this one. Okay, when it comes to this place, when you fit the model, generally what happens? The assumption is here, when you fit the model, the randomness will become 0. So now what happens here? Expected value of y is equals to, you have estimated, and this also you have estimated in such a way that to get this estimated value. Expected value of y means it is the average value. That is an average value. So this average value, whatever is there, it is nothing but expected value of y given x. This one. So it is expected value of your random variable y for the given value of x. Conditional probability, that one. We are estimating. This one is equals to beta naught cap plus beta 1 cap into x. This is the actually this one. Okay. So now you are estimating on an average only, you are estimating. So now when you come to my single variable, only one variable is there. So in that place, what is your average value? If I plot some 10 values are there, my average value is here x bar. This is the deviation from my average. But when it comes to regression, your deviation is this. Your deviation is this one. Your deviation. So what you are doing here, you are trying to find out the deviation from your original value is y and estimated value is expectation of y. This deviation we are trying to explain. So here in standard deviation, what you do? This is a formula you are using. Same formula only we are also using here, but in a next level formula to identify how much deviation is there. That is only we are calling mean square error, like that we are calling. So your standard deviation name will change in that place, mean square. So you will calculate that one. Whenever the standard deviation is less, all observations are near to your mean value. Whenever mean square error is less, almost all your original observations are near to your fitted regression line.
Average of all the distances.
Yes, average of this one. So that average of that one, the deviation, how much is there now? So that deviation, so generally if you see in, you can find this one in analysis of variance tables, ANOVA tables.
We are finding the best fit.
Yes, best fit. So whichever is mean square is less, that fit is the best fit actually. So that means on an average, this deviation will become less, almost all the observations are near to that. So the base is here only your mean and standard deviation only. But when it comes to here also, the average, you are estimating the average line here. But because of the relationship between the two variables, we are able to convert into a mathematical model. So that is the reason when one variable we are dealing, that relationships is not required. But whenever we are dealing with the different types of variables, some relationships we can identify and we can convert the relationship into a mathematical model and we can predict. So if you want to go for predictions, you need relationships is required. So this is very important for us. But if you don't want any modeling is not required means just you need to understand the situation means then this relationships is not required, mathematical equation is not required. Okay, so now I will come to the very important one, the inferential statistics, whatever is there. Why we are using this inferential statistics? So this is very important for us. This inferential statistics generally what it will explain. Statistical inference refers to making decisions or drawing conclusions about the population by analyzing the sample data from the population. So whatever I said in the sample data, so now you analyze the sample data and using the sample data, you try to represent your entire population. So how we are doing? Just I will explain here. Just one simple example I will take here. Okay, so here two are there. We need to estimate and we need to test. So whenever you are estimating the mean is there and using the sample data, you are calculating the some mean. But when you are using the population, so your mean is different. So your population mean is mu, for example. Your sample data mean is x bar. So whenever you are estimating population mean, there is definitely difference is there. That difference is negligible or not, that can be tested by using the inferential statistics here. Okay, so now just
difference between the
actual population value on sample data, sample. So now if you come to this place, say now my population is this, population characteristics we are calling as the parameters. In general, population parameters are unknown for us. We don't know about that one. Because now, every time the population is different. For you, population is different. For me, population is different. So one person may define the population is Karnataka state. Other person may define throughout India is the one population. So population parameters are unknown in general. So using that from that population, you draw some sample. That sample must be the representative of the entire population. Then you estimate the characteristics of the population. We are calling it in a statistics now. So this statistic you need to estimate. So now your population mean is there now. You are estimating by using the sample mean. Population variance you estimate by using the sample variance. Population standard deviation you estimate by using the sample standard deviation. But the question is here, population is a huge data and you are unable to estimate exactly in that place, then how you are going to test that one? The difference, whatever is there. Because in mathematics, if you say 10 means 10 only. If you say 10.0001 also, you won't consider it is equal. But when it comes to the statistic, how you can say that the maybe the difference is maybe some 2 is there, but statistics person will say that it is a negligible. So how it is possible? So that negligible, how you are saying na? So using the variation, standard deviation. Is that true? With the difference whatever is there, it is within the limits of your variation or not, that we are testing in that place by using the your sample data and this using the information statistics. Generally, we are using that one. Okay, so now just next one. Next. Yeah, so now, yeah, last one. Yeah, here we are for estimating, this is statistic, sample mean this. We have estimation theory is there and testing of hypothesis. It is useful to test whether this difference is negligible or not using the testing of hypothesis. Next. Okay, this is the last one actually. Entire theory, whatever you are doing, it is based on the sampling distributions, not with the probability distributions. So whatever you are calling, X is a random variable and the probability means specific probability is defined in that place. So whenever you are talking the statistics, first you never talk about the probability. I have some variable is there, 10 observations are there, you calculate the mean, you calculate the standard deviation, where is the probability in that place? You are not talking any probability in that place. So even if you have some 1 lakh observations are there with you and you want to calculate the statistic, you are not talking about any probability in that place. Whenever you are assigning equal chance for each and every observation, no need to talk about the probability because equal chance is given. So whenever you have given the equal chance, so that time what happens? Your mean calculation and other things all will become very simple in statistics. So maybe just I will take one example here. So I will go with next another one also. I have some 3, 4, 5 observations are there. Maybe in a class for students also I am using this. What is the mean for this one actually? Maybe 15 by 5. You will get 3. This one. So now actually what is the formula here? Actually let us assume that this is x1, this is x2, this is x3, x4, x5 like this. So now x bar means it is x1 plus x2, x3, x4 plus x5 by 5. This is the actual formula. We may think that it is a simple formula, just you need to add and you need to divide with the number of observations. But the logic behind this is the sample whatever I have selected from the population has an equal chance to select the data. Maybe you have 100, in 100 first one is equal chance, second one, third one. So now what happens this one? x1 into 1 by 5 plus x2 into 1 by 5. So like this, we have n observations also, 1 by, maybe 1 by n, maybe 5 are there, 1 by 5. Now actually the chance is this. and now your original value is x1, the probability of selecting this x1 is this. This is, we are multiplying here with the corresponding probability in that place. So like this, you are calculating. So finally, your mean value is actually your formula you are talking about xi into p of xi. So this is the original formula actually. But whenever you are talking about the statistics in that place, by default we have given equal chance for that observations. So for that reason, no need to separately explain that one, the probability is given. But until you are talking about this variable will follow some specific distribution, until that, no need to talk about the probability in that place. Once you say this random variable is following some specific distribution, then that variable will become as a random variable. So whenever the variable is there, actually it is the realization of the random variable is the variable actually. You have the values are there. In that place, equal probability by default we are assigning, we are calculating simple formulas, so we are calculating everything comfortably. But when it comes to a random a variable is x is following some specific distribution, for each and every value there is some specific probability is assigned. In that case, what happens? Your variable will become a random variable. So your modeling predictions, everything is for your random variable, not for the variable, because specific probabilities are assigned in that place. Okay, so now the probability distribution of a statistic. Generally, now when it comes to the probability, so now what you said, random variable is there and specific probabilities are assigned in that place, then automatically you are calling it as a probability distribution. Okay, for example, I have my random variable is x is there and there is some specific probabilities it is assigning. So together we will call it as a probability distribution of the random variable x. So now what happens? This is a general term. So here maybe if the x is following a binomial distribution, p of x is the probability function, some different function is there. Maybe Poisson distribution, different function is there. Normal distribution, different function is there. So if you assume maybe if you replace the values x value as 1, 2, 3 like that, specific probabilities you will get in that place. So now what happens? You are not dealing with the probability distributions directly because the sample data only you are taking. Now your sample data, whatever is there, that you are trying to understand whether that data is following that particular probability distribution or not. You are trying to understand that one. So in that case, what happens? To test whatever I said, the original population value is there, parameter value, sample value, the difference is there. How you are going to test? The sampling distributions plays a major role to test that one. Okay, only one example I will take now. Yeah, okay, only just 5 minutes. Only one example I will take and I will close here. Yeah. Okay, let us assume that my population has 5 values, 5 observations. I have only 5 because even a statistics person, when theoretically when they are going, it is very difficult to understand. Theoretically maybe, you go empirically, then anyone can understand. My entire population is having these values. Only 5 values are there. So now we are dealing with the sample data now. Okay, let us assume that you take 3 sample data from this that need to represent your 5 observations. It has to represent 5 observations. I need 3 observations. So now this population is there. My population mean is equals to, now what happens? Add all the observations divided with population mean I can get. So now this is a 3, you will get 3, 1 plus 2 plus 4, 5 by 3. You will get 3. Now you select a sample 3 in such a way that the mean must be 3. You have to get. Then only the sample data, whatever you are dealing with, so the sample data will represent your population characteristics. Then if you get 3, then the sample is very good. Otherwise, maybe you are getting maybe less than 3, greater than 3, that sample may not be a good sample. So now what happens? For example, you need to consider here, so that is the reason generally what happens, there are 2 things are there. When you are selecting the sample, your sample may overestimate, underestimate. These 2 things will happen. So we must be very careful in that place. So now let us assume that maybe order is not important, combination only. 1, 2, 3 means 3, 2, 1 or maybe 2, 1, 3 all are same only. So now how many combinations I can bring here? This one. How many combinations? So now I have 5 are there, 5 are there, and 3 I need to bring. So 5 C3. So how many? So 10. 10. So 5 factorial. So 5 to 3, 3 factorial, 2 factorial, 4 into 5 by 2, 10. I can get 10. So now 10 combinations I can write. Okay. So let us write that combinations. Combinations you write down. So first one, for example, you have collected 1, 2, 3. You have collected 1, 2, 3, 3 observations. So maybe one student selected 1, 2, 3. He said this number will represent the entire population.
2, 4.
Okay. So now next one. Okay. So 1, 2, 3. What is the mean for that one? Average value 3, 4, 5, 6. 6 by 3, 2. Mean. So sample mean only. Yeah, sample mean. But actually original mean is 3. So he selected a sample 3 that is representing 2. Now I will go with okay 1, 2, 4. So 1, 2, 5. He selected another sample. So now let us go with 1, 2, 5 is completed. 1, 1, 3, 1, 3, 4, 1, 3, 5. So maybe 2, 3, 4, 2, 3, 5. So now next one is 3, 4, 5. So 2, 3, 5, 2, 2, 4, 5 is there, no? 2, 4, 5, 3, 4, 5.
So, but itself is a sample, no? 1, 2, 3, 4, 5 itself.
No. I'm assuming it is a population.
Oh,
I have only the population has only 5 because for understanding. Yes, only my population has only 5 units. Let us assume because population is huge, but to understand that one, just take only 5 units.
population.
So generally population is capital N, maybe it is a large. So now I am taking this is 5. My sample size I am taking 3. Sample is 3. Okay. So now second one 4, 5, 6, 7. So 7 by 3, how much you will get? Some what is the 7 by 3? 2 point something. 2 point. Okay, 7 by 3 here, and actually this 9 by 3 this one, and 8 by 3 this one, and
9 by 3. 6 by 3.
oh, yes. Okay.
Number
So this
population.
6 by 3, 7 by 3, and it is
8 by 3.
8 by 3,
8 by
8 by 3.
again 8 by 3. So now 5,
9 by
9 by 3. So now this one
9 by 3.
9 by 3 again. Yes, this one is 10 by 3, 11 by 3, and now this is 12 by 3. 12 by 3. Okay, now you convert into a probability distribution. So in all the places, if you see this, how much this 2? It is 2 point something. So 2 points. So maybe for example, student you can calculate what is 7 by 3? 2.33, na? Oh. 8 by 3? 8 by 3? 3 point? 2.66. 2.67. This one? 2.67. Okay. Here? 3. And now this one? 3. This one? 3.33 something. This one? 3. For something 6, 7 like that. It is 4. Now, luckily, if you get this sample, if you get this sample is the best sample for us to represent the entire population. You will get. So, if you get this samples, it will underestimate. So, in real time, what we are doing, we are not going to do this many combinations. That is the reason now machine learning, other things came, different combinations that will check. Which one is getting near to your population, so error is less, that will pick that one. So here, if you collect this sample, if you are getting this sample now, then this sample is very good. So if you get this, automatically you can represent entire population, it is good. But maybe if you get, you are an unlucky person, because it will overestimate too much. And overestimation means you may say that, okay, this student will get out of 100, tomorrow he will get only 70 only. This is a problem, overestimation. And this, if he gets this nut, this will represent maybe student will get only 60, but he will get 95. So it is a underestimation. This is a overestimation. So it is a original estimation. So here what happens? So the sample, whatever we are collecting, this will play a major role. whenever you are collecting the data. That is the reason every time we will ask the sample what you have collected that needs to represent the entire population. Such that in such a way that you need to collect the sample. So the logic behind the what is that? The fundamental logic behind the big data analysis is whatever the data you are collecting, that data need to represent the entire population. This is the major one. So now what happens? The inferential statistics, what it do? So here the question will come. Inferential. For example, I got this sample. I got this one. Now it is a 3, it is a 2.67. So somebody will say 2.67. If I round up that one, 3 will come almost, and it is near to me. So you consider me like that, they can ask. So other person, mathematics person will say, no, 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 it is not equal. So other person, social science person will say, okay, level, okay, you make 3, like that. So now the question is, both persons I need to satisfy. Is this is equal or not, I need to tell. So now what happens? This difference, your entire population is there, and maybe the sample, whatever you got, the difference, whatever you got, this is the error. This error is negligible or not, I need to test now. Means, how I can test that one, it is negligible or not? Now, my question is, this error, see, generally what happens now, if you go to medical sciences, medical diagnostics, maybe you went for blood test like that, you may get some report, your blood level is some 11 point something. And maybe if they go with the mathematics way, 11.6 is less than 11.25, you have more blood levels are there, you take a treatment. So, but it is not required actually, because for one person different, other person different, so other person different. There is some deviation is there. That deviation we need to accept that. In real-time applications, we have to accept the deviation. So that is the reason this deviation, whatever is there, na error. So this inferential statistics will tell you is this deviation or we call error, it is negligible or not. It will calculate and it will test. So that we call as the testing of hypothesis. In testing of hypothesis, we will test whether my hypothesis is this one, whether my population mean is equals to this 3 or not. I will test this by using this sample data. I will test that.
What's the name? The testing of
Hypothesis. Testing of hypothesis.
Deviation between the actual and
Yes, actual and sample. Using the sample, statistic, whatever you got. To test that, you need to create a hypothesis. So you need to test the hypothesis, whether that is negligible or not, you need to test. So in inferential statistics, we have number of tests. So this inferential statistics is more useful. Daily we are using in medical sciences. So to test whether the drug is effective or not, after testing validity of the results, then only it will come to the market actually. So these are the, what is that, whether central tendency, variation, and the symmetry, and the testing of hypothesis. These are the backbones for data analysis, data science. If we are very strong in a place, you can test and you can give the conclusions for the entire data set also. So that is the reason we call it is just only 4 to 5 base in statistics can explain the big data also, and you can understand everything in that place. So before going to the modeling, you need to understand the characteristics. Only this only enough to understand. Maybe small other things are there. So these are the fundamental logics. So that is the reason I call it is a foundational logic behind the big data analysis. It is a small data or big data, this only will work. So this is the base for your data analytics. So maybe you can go for data analytics, but the base we must know about this. So that is the reason maybe now we can see probability statistics we have introduced means all this covers in that place. So but maybe inferential statistics it needs to more. Yeah. Okay. So with this, I will close here. Any queries are there?
So how do you decide the sample size?
Yes, sample size. See, this is a one question actually. So for example, your population has some 1,000 are there. How much sample I need to take? So in that case, what happens? There are two things. One is you can maybe like rule of thumb like that. So you can go, okay, I can take some 5% or 10% like that. You can do. Otherwise, specific formulas are there to define using the what is that variation, other things. So you can include in that place automatically you can get the sample size in place. So we have to do
After certain, there is saturation also happen. If the sample size is too much, also the saturation also happen.
so sample size is too much means, for example, now I have 5 of the population. So if I take only 3, I can get near the 4 if I take now, almost all I can get to the population being near to that. So maybe generally what happens, because you are dealing with the large data sets, so whatever is there, the large sample data maybe, so it is like, if it follows the symmetric distribution, then automatically it is a good sample.
Rule of thumb is there.
Yes, yes. You can do that. So with this I will close. Yeah, this is the testing of hypothesis as I thought.
Any other questions?
Already done.
I thank Subramanya sir for his work. So we will end the event for today. Hope to meet you in D505 tomorrow.
Tomorrow D505, so you come that place. And for all of you, tea is there, tea biscuits you take. Everyone is there.
Everything done.
Sorry.